The primary advantage of unsupervised learning is the ability for a machine to tackle problems that humans might find insurmountable either due to a limited capacity or a bias. It is ideal for exploring raw and unknown data. Understanding this, we have come up with this unsupervised learning tutorial. Now, before we go ahead with the session, I'd like to inform you folks that we have launched a completely free learning platform called Great Learning Academy, where you have access to free courses such as AI, cloud, and digital marketing. You can check out the details in the description below. Now, let's have a quick glance at the agenda. We will start off by understanding about unsupervised learning, then we will learn about PCA. After that, we'll have a demo on PCA. Going ahead, we'll learn about k-means clustering. Finally, we'll have a demo on k-means.
Today I'm going to take you through a very important topic called PCA, Principal Component Analysis. But before I go into PCA, since it is also based on mathematical transformations and all, I thought I'll spend a few minutes with you on some mathematics part. Okay. But before I go there, any questions from yesterday's exercise? Any questions? Yes.
Okay. My question is, you were talking something about convex functions yesterday.
Convex functions, yes.
And it was like, in that case, you have 2 points and you are drawing the line between those 2 points. If the function is not convex, you were talking that there could be different points on a single line. Means you could have a situation where you have number of points on a line itself, the SVM line. In that case, how do you decide the best line?
You're talking about, if I understood it right, you're talking about this case. File SVM. Are you talking about this diagram? Are you talking about this?
Yesterday, someone asked a question about there could be number of points on a line itself, and you said that it is possible if it's not a convex function or something like that. And if that is the case, then my question was, there could be a line which has 3 points on it, or a line which has 4 points or something like that. Then in that case, how do you decide which is the best one to?
I'm still not getting you. What do you mean by lines on, points on the line?
Like support vectors. Currently you have
support vectors.
Yes.
Okay. Support vectors. Lines on the margin. Points on the margin.
Yes.
Margin, you're saying.
Not exactly margin, but you could have it on those points also if it's very dense. Something like this. In that case, you have means if you look at the bottom one.
Bottom one.
You have on that particular line only you have 3-4 points or 3 red dots or.
You're talking about the line means the hyperplane.
Yes, hyperplane.
Okay, fine. So what is the question?
So in that case, how do I decide the best one? Means because there could be a number of them. So.
Oh, you're talking about in soft margin case, how do you define the best lines? That's what you're asking, yes. Right? What you're saying is, your data points have jumped into the margins. Now within the margins, your data points crossing the margin, sitting on the line and all those things, how do you define the best line? That's what your question is. Okay, see, you're saying that some data points can be inside the margin, some can be sitting on the line. How do you decide the best fit line? Okay. Now, when the data points are not linearly separable, you will never be able to find a support vector machine with hard margins. That is ruled out. Okay. So what is the next best thing to do is, okay, go for soft margins. Now I wanted to give me a line which has margins equally on the both sides, but the line should be inclined in such a way that a minimum number of data points fall within the margins. One hand, the margin should be the largest possible. On the other hand, the number of data points within the margin or sitting on the line, whatever it is, should be minimal. That's what we call a slack. So I wanted to give me a combination of these margins and this line using whatever angle you like, such that minimum threshold, minimum slack, max margin. When you put these two conditions of minimum slack and max margins, that is what this is, minimum slack plus max margins, then you'll see that there is always only one best fit line there also. You can't have multiple solutions. The reason why you can't have multiple solutions is, look at the nature of this function. It is quadratic. Look at the nature of this function, it is a plane. This is called affine. In mathematics, we call it affine constraint, which means a straight plane, while the other plane is quadratic. Okay? Now, when I combine these two, so the dimensions I'm going to show you only two, because we can see 3 dimensions only. So we have 2 parameters, W1, W2. Now, given W1, W2, the quadratic, this one, it takes the shape of a bowl. This is called convex function. This is the shape you will always get. Simple, you take any x-axis, take any number over here, this is 0, 1, 2, 3, 4, 2, 3, 4, minus 1, minus 2, minus 6. When you plot x square, this is x square. X square is same as w square, right? For any w, you will see that the shape is always a bowl. Negative into negative becomes positive. So it becomes a bowl shape, okay? Such functions are called convex. Now you have a convex function here, and the constraint that you have is a plane. On the same input parameters, I am looking for a plane. So when I combine these two into one single problem statement, what it means is, in the mathematical space consisting of these w's and b's, find out that point where the plane and the surface, they touch each other. And as you can imagine, there can be only one point at which the plane will touch the surface, the quadratic surface. Hence, you can have only one solution to the problem. That point where it touches, the combination of w's is the line, the best fit line that you get. Right? So whenever you have this soft margin case, even there you will have only one best fit line which meets both these criteria. Right? Okay. I know it was a bit kind of overwhelming yesterday. Support vector machines, support vector classifiers with all the mathematics behind it. Any questions before I jump into this PCA? Because PCA was also slightly mathematical.
Then how the Slater's condition comes after that, the dual, right?
A Wolf dual. Okay. What Slater said is, whenever you have this case of maxima and minima, okay, so for which I took a very generic diagram yesterday, you have one function which you're trying to minimize, you have another function which you're trying to maximize, where the function is the margins from the plane. I want to try, if I plot that, another function which I'm trying to maximize, what Slater said is, this is called the primal, this is called the dual. If you are meeting that condition, which is called, what is the name for that? Strong dual, STRNG, strong dual case, what he said is, solve only one. Whatever solution you get for one will also be a solution for the other one. So what this guy said is, either you solve for the minima, wherever the minima happens, there the maximum of this will also happen. You don't need to solve both. Advantage of this is, many times solving for the minima is not easy compared to solving for the maxima. You solve for the next one. Right? So that is what Slater's condition is. But you have to meet certain conditions to be able to do this. Fortunately, support vector machine, the optimization function, it meets that requirement. Principal component analysis belongs to a family of data transformation techniques, which are called matrix-based data transformation techniques. There's another very similar to this, singular value decomposition, SVD, which is a matrix decomposition technique, right? Then we have ICA, independent component analysis, which is similar to PCA, principal component analysis. So there are various techniques for transforming your data. The most often used technique is PCA, right? I would advise you to go and also study about the independent component analysis, ICA, which in my view is slightly more stronger than PCA, but for some reason PCA rules the industry. Okay. And useful concept, but you have to apply it with great care. It may not always give you the return on investment. A lot of people think that PCA is a silver bullet to all the problems. It is not. So you need to know when to apply and when not to apply. To understand the concept of PCA, it's okay. Let's start with the discussion first. This is all not later. We'll deal with this later. Which radio station do you listen to? Yashaswini. 93.5. Which station is this? Radio Mirchi? Something of that sort? I don't know. Okay. Radio Mirchi. She listens to 93.5 FM. Looks like she doesn't actually, but she says that she listens to 93.5 FM. Okay. Now the question to you is, did you ever notice that when you tune your radio to 93.5 FM, you get the loudest signal from the station? But you can listen to this station even at 93.4, 93.3, 93.2, so on and so forth. Have you noticed that? You can listen to a radio station even slightly when you tune your thing slightly to the left or to the right. But as you move more and more towards the left or more and more away from the point, something starts happening to your signals. What? Unwanted signals. Your radio starts capturing unwanted signal. I wanted to listen to 93.5 FM, but now it's getting mixed up, jumbled up with signals from other stations also, which we call noise, the radio noise, right? So in short, if I plot the energy in the energy means the amplitude with which you're listening, then you'll see that the signal of interest to you is spread over a range of frequencies. The signal of importance to you is spread over a range of frequencies. Are you all okay with this? In electronics, when you study electronics or in statistics, we say that your signal is stored in the spread. So the variance that we have been talking about, xi minus x bar raised to power 2 by n, that variance is basically a representation of how much information has been stored on that particular dimension. So information is stored in the spread. Okay. Now, how does this happen? Your radio station, it starts to send the waves at 93.5 FM. But by the time it reaches your radio set, in between, a lot of factors come into play. The density of the air or the waves bounce off the buildings and so on and so forth. A lot of factors come into play, because of which what started as 93.5, in fact, because of the various equipments inside the station itself, what started as 93.5 will reach you as a range. If I had a perfect radio where it will catch 93.5 only at 93.5, only when you keep it at 93.5, then you'll listen to your songs or your station in breaks. The reason why you'll listen to your song or your radio station in breaks with gaps is the signals are not always coming to you at 93.5. Sometimes they're coming at greater than 93, sometimes less than 93. So your radio has inbuilt what is called a band filter. As you would have guessed what the band filter does, it eliminates all the noise and takes the signal of interest to you, the 93.7 FM. Then it goes to amplifier. From the amplifier, you listen to your songs. The reason why you listen to your songs continuously is the band filter removes the noise and captures only 93.5 FM from the spread. Of course, it will not be able to do beyond range, right? So the concept is my information is stored in the spread. From that spread, I have to extract the information because larger the spread, the information is mixed up with unwanted signals, noise. How do you do that? That is what PCA does. PCA is a technique to improve your signal to noise ratio. In radio terminology, it's called SNR, signal to noise ratio. The whole objective of PCA is to improve signal to noise ratio. Very surprisingly, many experts, domain experts, they unfortunately, they kind of slightly, in my view, mislead when they say that PCA is for dimensionality reduction. PCA is not, you can do dimensionality reduction, but the main objective of PCA is improve signal to noise ratio. What exactly this means, we are yet to discuss. The secondary objective of PCA in data science can be to reduce the dimensionality of your mathematical space. You're constructing a model in data science, okay? And in that model, I'm going to do m.fit. Remember, we do this in training, m.fit during the training stage. So during the training stage, we do m.fit and we supply x1, x2, so on and so forth. Let's assume only x1 and x2. All of you okay? All machine learning algorithms, and of course the target variable. All machine learning algorithms, they assume that between x1 and x2, there is no covariance, there is no relationship, they are independent of each other. Are you aware of this? All algorithms, they expect their x1s and x2s to be independent of each other, not influence each other in any way. There is only one algorithm which unfortunately gets a bad name, naive Bayes, where it assumes that all features are independent of each other, but in reality they are not. Hence it gets the term naive. But then all algorithms assume that features are independent. You don't call naive linear regressor. Right? Unfortunately, only one algorithm gets that name. So when I do this fit function and supply these parameters, what you're essentially supplying is the central value and the variance of x1, then central value and the variance of x2. You're supplying this to this. And you're trying to figure out, is there any hidden pattern relationship between the target variable and these two based on this information? What you're missing out is, we know in reality x1 and x2 are not always independent. Which means if I plot the data in a two-dimensional mathematical space, I might see maybe some weak trend somewhere. They're not really independent. When you plot this, I get the variance in the spread. When I plot this, I get the variance in the spread. I am supplying this information and this information. I am supplying these two to the model. What I am not doing is, I am not supplying this covariance information to the model. There's such a rich information stored in a mathematical space which we call covariance. How x1 and x2 influence each other. How because of a small change in x1, x2 changes and the reverse. That information we have not supplied to our algorithm anywhere. And we know that the information is in the spread. So you're given this spread, but you're not given this spread. That is where the max information is. So what PCA does is, PCA tries to create a composite dimension which covers the max spread and another dimension which covers the next max spread, and the two original dimensions are dropped. So now you have two new dimensions. You rotate this. So now between these two dimensions, all the spread has been captured. There is no hidden information in the mathematical space. You have really transformed them into two independent dimensions. Now feed these two dimensions, PC1, PC2, feed these two to your fit. The algorithm gets much richer information to work with. Out of that covariance, I can extract the variance of x, I can extract the variance of y if I need to, right? So now your algorithm gets a much richer information to work on. This is the concept of PCA. Hi. So if originally you had two dimensions, PCA will give you two new dimensions. If originally you had 30 dimensions, PCA technique will give you 30 new dimensions. And it will make sure that all the 30 new dimensions are independent of each other, which means there is no covariance between them. So all the information in the original mathematical space, it gets absorbed like a sponge by the PC dimensions. And you make use of your PC dimensions to build your model. Her question is, what is the difference between covariance and correlation? Correlation is covariance by standard deviation. Measuring the covariance in standard deviation units, that is called correlation. Now, if originally you had n dimensions, you will get n PC dimensions. What you will notice in these PC dimensions is, the first dimension that you get captures the maximum spread. The second dimension which you get captures the next maximum spread. If you had 3 dimensions here, and this distribution was like a rugby ball, a 3-dimensional rugby ball, yeah, then you'll have a third PC dimension here, where rest of the variance in the data points in mathematical spread would have been captured. So with every PC dimensions, the amount of spread that they capture from the original mathematical space, it falls. You will see a fall, okay? The first PC dimension will cover the maximum spread. Next one will be next, PC3, so on and so forth. It will fall. Information is in the spread. So all these PC dimensions here, which are capturing very small spread from the original dimensions, they are representing very small pieces of information from the original dimensions. It might be okay to drop them from your analysis. By dropping those PC dimensions, you're not losing too much of information. You're losing information, but not significantly. So you might want to drop those PC dimensions. This is what we call dimensionality reduction using PCs, principal components. The advantage of that is, without losing too much of information, you're reducing the dimensionality of your mathematical space, so computationally advantageous. Second, you are moving away from curse of dimensionality. More the dimensions, more you're going to suffer with variance errors. So when you're reducing your dimensions, you're moving away from that curse of dimensionality. You're moving towards the right fit. Are you all okay? By the way, point which I will not be covering, but I would like you to do a homework on this if you wish. There is a variant of PCA called, what is it called? What do you call random functions in statistics? Stochastic PCA, okay? Stochastic PCA is designed to exactly solve your problem, Prakash, right? So stochastic PCA randomly creates PCAs using random data points. The problem with the PCA that we are going to use is it will load all the data points in the memory. So if the data is huge, you will end up with out of memory errors. Right? All right. Any other question? Bring it up. Let's move. So it begins by standardizing the data. That is what we call centering of the data. All the dimensions are subtracted by central values and divided by standard deviation, z-scores. Once this is done, a covariance matrix is generated, where covariance matrix basically represents the information in the mathematical space. On that covariance matrix, what this covariance matrix is, I'll tell you in a minute. We will generate a matrix. In this case, we have only two dimensions, x1, x2, x1, x2. This is a covariance matrix where on x1 axis, what is the variance? On x2 axis, what is the variance? And between x1 and x2, what is the covariance? That will also come here. Between x1 and x2 or x2 and x1, the covariance, these two will be same. It will be symmetric matrix. Above and below will be same, right? This is called the covariance matrix. And you have already seen this matrix many times. Pair plot. Pair plot is a visual way of representing the covariance matrix. Convert the pair plot into numbers. What you get is a covariance matrix or a correlation matrix, which actually numerically represents this. So, now that I got this out of my centered data, we'll apply a process to it, transformation process. The transformation process, what it will do is, it'll convert this into another matrix, where in that matrix, you only have these two numbers, these two become 0. When these two become 0, that means it's representing a mathematical space where there is no information here. And it will also give you two other matrices. These matrices are nothing but your eigen dimensions. These are your principal components, PC1, PC2. This number represents the spread on PC1. This number represents the spread on PC2. It's the spread, the variance in PC1 and PC2. So let's see how all these things happen. Once again, you may want to get into the mathematics if you need, if you require, if you think you'd like to know, or you can remain at the conceptual level. Leave it to you, okay? The PCA, effectiveness of PCA, a lot of people criticize PCA. There is a vertical split amongst data scientists. Some of them criticize PCA, they said it's a useless thing. Some of them support PCA. Just like p-values in statistics, there's a vertical split between the statisticians. Some people say p-values are useless. But some statisticians, they take it as religious, p-values, right? So there's a vertical split, unfortunately, even on PCA. The reason why people oppose PCA is the principal components that you come out with will get impacted if you change the scales. If you change the scales of your data set, then the principal components that come out will be totally different. But then this objection does not hold water because we are anyway going to convert them into z-scores. That is the argument given by the other author. So what is the problem they ask? In p-values, the problem with the p-values is the assumption that these dimensions are independent of each other. That assumption is violated most of the time. You are all aware of p-values, right? Go and check for yourselves that when you drop a useless dimension, this p-value is it's not useful, it's greater than 0.05, the p-values of other dimensions change. When you have dimensions which are multi-collinear, you drop one, the coefficient of the other changes. I want to try out what is the relationship between the independent variable and the target variable. This relationship, which you call coefficient or slope, it does not hold, it changes when I bring another dimension into play. So the p-values get impacted. So many statisticians say p-value is not reliable. They use Bayesian probabilities to establish the reliability of the dimensions. I'm deviating here a bit. This is just to inform you. Same way, PCA, there is a vertical split in the data science community. Some people say it's reliable, some say it's nonsense. Fortunately, the majority is it's reliable. So you might find many papers on the web which says why PCA should not be used. Right? However, from the point of view of the interviews and all, these guys love to ask questions on PCA. What is PCA? How it is used, so on and so forth. You cannot interpret your PC dimensions. Of course, you can find out what is the contribution of original dimensions to the PC dimensions. That we can do. Outliers can completely bring your PCA to the knees. As you can understand why. If there is an outlier here, your PCA dimension will become this. So outliers can completely bring your PCA dimension analysis to its knees. So you need to be careful. PCA assumes, this is your question. PCA assumes linear relationship between attributes. PCA works in this kind of environment. PCA cannot give you any good results if the relationship is there but it is not linear. PCA will not help. Okay? So when do you apply PCA? Only when you see collinearity between dimensions. And you're in a situation where you want to reduce the collinearity and at the same time you want to reduce the dimensions also if you want to. I'll cover this in a while. We'll do the hands-on in a while. Let's look at the underlying mathematical constructs. So keep in mind the original objective of PCA, principal component analysis, is to increase the signal to noise ratio. So I can convert my original dimension to PC dimensions and build a model on the PC dimensions without dropping any dimensions. That is likely to give you much better results, scores, than what the scores you got in the original dimensions. However, many people use PCA to reduce dimensionality. In data science, you will often see PCA by default dimensionality reduction. It has become that now. This is what we are discussing. So I have the original dimensions. You have the spread of the data point on this, spread of the data point on this. So when I build my models using this original dimension, I'm giving only this much information and this much information to my algorithm. What we do is, we measure the covariance hidden in the mathematical space using covariance formula. All of you know covariance formula. Do you know variance formula? Variance formula. Xi minus x bar raised to power 2. Why raised to power 2? Because plus and minus variance, they will cancel each other, or otherwise you will get 0. So xi minus x bar raised to power 2. I want to find out the average variance on this dimension. There are n number of points. So xi minus x bar raised to power 2 by n. That gives me average variance on a given dimension. Average information content on a dimension. That is your variance. Okay. How do you find covariance? Replace xi minus x bar with xi minus x bar into yi minus y bar. That is called covariance. The rest of the thing remains same. Divide by n. When n is very large, you can divide by n. When n is very small, we divide by n minus 1 because n minus 1 is called degree of freedom. Do you understand the concept of degree of freedom? Yes or no? Okay. So you can divide by n when n is large. When you do this analysis, the output of this analysis will be a covariance matrix. And to do all these things, we have pre-built functions in our this thing, what you call scikit-learn, which we'll make use of to find out the covariance matrix. On this covariance matrix, which represents this original mathematical space, I'll apply a transformation called eigen, EIG. EIG stands for a function called eigenfunctions. Eigen is a German word which means unique. So given mathematical space, there are only unique set of PCs. You can't have anything else as PCs. There are only one particular set of dimensions which are your PC dimensions. So first, we center our data. We convert it into covariance matrix. We apply the eigenfunction to this. This is converting to z-scores, finding out the covariance matrix. On the covariance matrix, we apply the eigenfunction. When you do this, what you're essentially doing is rotating your mathematical space to find out the PC1 and the PC2. Now this PC1 and PC2, when I recalculate the covariance matrix of PC1 and PC2 will have zeros. Only variance will be in PC1, only variance will be in PC2. There will be no covariance. This is called the diagonal matrix. So if I try to find out the covariance of this, what will happen is you will have only these terms. All these terms will become zeros. So when you have a diagonal matrix representing covariance between two dimensions, that means they are truly independent if they have zeros here. Okay? There you go. This is my PC1, PC2. In technical jargon, we'll call this eigenvector 1. This will be called eigenvector 2. And the spread that you see here, this will be called eigenvalue 1. This spread which you see here will be called eigenvalue 2. What happened? Seriously sure? 100%? Yeah. What we call PC1, PC2, technically it's called eigenvector 1, eigenvector 2. And the amount of information captured or absorbed by them, that is called eigenvalue 1 and eigenvalue 2. So if you have 100 PC dimensions, you will have 100 eigenvalues. Okay, you want to know what he said? It sounded like Greek, right? This is my original mathematical space. All right? So the line connecting the farthest points, that line, I can treat it as an arrow, a vector. I can do that as a vector. Can I do that? Yes or no? Okay. So, this is, okay. If I have a vector, this has some length, let's call it L. It has some direction. Okay, the direction is given by the angles. All right? So it has some length and some direction, magnitude and the direction. I can always represent this vector as a unit vector where the unit vector has a length of only 1. Okay, length of only 1. So I can always say unit vector, which is this one, into some value val will give me back the original vector. I'm scaling the unit vector and bringing it to the original size. This value is what we call the variance, the eigenvalue. Right? Yesterday, remember in support vector machine, I told you geometric margin is functional margin divided by length of the W. We converted into unit vectors there to compare the different slopes, different planes. Remember that? Same way here. So I have a vector of certain length and certain direction. Without changing the direction, keeping unit length, when I multiply this with some quantity, it gives me back the original one. This quantity is what we call the variance, eigenvalues. So your principal components, mathematically, they are all unit vectors. Unit vectors multiplied by the eigenvalue will give you back the original dimension. Right? Very interesting concepts, but unfortunately difficult to grasp if you're not already aware of some things that go into making all those things. Okay, now look at this. Now I feel the amount of spread in the eigenvector 1 is quite large and a significant portion of the original spread in the mathematical space. The spread captured by eigenvector 2, the principal component 2, it's a very small, tiny part of the original information. It's my choice. I can completely drop this dimension. I can say, forget the eigenvector 2, let's not use it for our analysis, let's keep only principal component 1 or eigenvector 1. I can do that. So I build my models on a reduced number of dimensions. But whenever you drop any principal components, howsoever small information it may have, you are losing information. But the amount of information lost versus the gains I get in terms of computational speed and the variance, reduction in variance errors, the amount of gain I get overrules the amount of loss I face. So in such situations, I might drop my PC dimensions. Shall we move on? Any questions? Yeah, it's unique. That's why it's called unique. If you do independent component analysis, there you should see the eigenvectors may not be completely independent of each other. I will not be covering that here. I don't have material on that, but you should be aware of that also. Anyway, let's move. Oh, by the way, I came across a very beautiful site to understand the principal component analysis. Really, I mean, you will see it for yourselves. PCA explained visually, right? So if you go down, this is what it is. Three-dimensional mathematical space where the data points are scattered with some covariance in the mathematical space, right? The original 3 dimensions are shown here. What PCA does is, PCA rotates the mathematical space, and my PC1 is red, so it tries to, you can go around and play with this. This is very cumbersome, mathematically it's so elegant and beautiful. This is what it tries to do. It tries to represent the PCA covering the maximal variance in your data. PCA2 and PCA3 cover the rest of the variance in the data set. And it's guaranteed that all the PCs will be perpendicular to each other, orthogonal to each other. So if you look at it, in the original mathematical space, on dimension 1, dimension 2, dimension 3, now in PC dimensions, dimension 1 captures the maximal spread, dimension 2, dimension 3. Right? Please go through this site when time permits. He's explained it through visual diagrams and plots. You can play around with these plots, they're dynamic plots, and understand PCA better. He's also given calculations here in case that interests you. We'll do this hands-on and see how it works. Questions? Shall I move on? If you observe carefully, the red PC covers the maximum spread, followed by the green PC. There you go, it's coming out now. It covers next maximum spread, followed by the third PC. In fact, third PC is the blue one, right? Yeah, third PC. In fact, blue one captures maximum spread than the red one. Than the green one. So what will happen is, it will sort this on the basis of the spread. It will sort it. And the first one is always the max. Second one is the second PC. Then you'll get the third PC. That spread, that sorting will happen automatically. You'll see that when you do the hands-on. If you notice the PC1, there are 3 clusters in it. Since you people have done k-means clustering, you're seeing 3 Gaussians in it on PC dimensions. We also make use of PC analysis when I have multiple Gaussians in my data set. I want to convert approximate Gaussians out of the 3 Gaussians. This is also used, PCA is also used there, right? But generally people are not aware of this. PCA and clustering, they're very strongly related. They're very strongly related to each other. Anyway, I'm going to move to PPT. Just a few more bits of concepts. This, I actually made it this morning because yesterday after understanding the challenges, I thought I should put it visually. It's a simple code. You can also try this code out. I'm generating, based on random function, I'm generating some random numbers. 2 into 2, okay? So this is my 0.5928 randomly generated. This is one record, this is another record. In your data frame, you have only 2 records. This is my data frame. In the data frame, I have 2 records. Record 1, record 2. The values of the first record is 5928. 5928. I told you yesterday that many people refer to this as the vector space. They don't call it mathematical space. Why do they say that? I can always represent this 5,8 as a vector over here. This is 5,8. This is 2,8. This is a vector, second one. So this arrow represents the second record. This arrow represents the first record. So every data point can be represented as a vector in the mathematical space. Okay? This data point, what you see here, what we call data frame without the column headers, in mathematics we call them matrix. In scikit-learn Python we call them arrays. Okay? So this can be represented as a matrix. So I'm going to call this matrix M. Then there is a corresponding matrix called MT. MT means transpose. Transpose operation, what it does is, it makes this as 5928. Rows become columns and columns become rows. Why do we do this? We need to do this to do one particular mathematical operation. A matrix based operation. Okay, that operation is nothing but M dot, that is multiplication, M transpose. Don't worry about this. There's a mathematical operation called M dot M transpose. What exactly does this mean? That is what I'm trying to explain to you. Okay. So if this is my matrix M represented in vector space like this is my M transpose. All you need to do is put a T over there, it'll transpose it, which is my represented in vector space like this. When I do this dot operation, look at the dot operation. This dot operation, I'll do it here. 5298. Okay. This dot operation, what happens is you multiply this and this, 25, 106. Hey guys, you have to give me the number. 9 9 is 81. 81 plus 25 is 106. So this becomes 10 plus 9 is 72, 82. This will be 82. This is 4, 64, 68. Is that correct? 68. Now this, what you've done here, this is nothing but xi minus x bar raised to power 2 by n, which is 106. Yi minus y bar raised to power 2 by n, which is a 68. And what you see off diagonal, this is the covariance between these two. So when you do a dot operation on a matrix in Python, what you're basically doing is building a correlation or covariance matrix. And this is nothing but a pair plot. Shall I move on? Shall I move on? Okay. We are going to do some dot operations in our code. So I hope you understand what the dot operation means. Okay. Now before I move on, I forgot. So this is again important, so I thought I should cover this up. Yesterday, we did a dot notation there, okay? When we applied or we supplied the x and y variables into the equation of a line. Remember that? When you put the x and y variables of a data point into equation of a line, it gave us how far away it is from the line, either on positive side or negative side. Remember that? That is also called dot notation. That is also dot notation. So imagine your line had a coefficient. Imagine this is your line. I've created another data frame df2, again using some random functions. Imagine this is the coefficient. m1, m2 or w1, w2. Okay. And then I'm doing, look at this, df1 dot df2 transformed. Please observe this line. df1 is this data frame, which is nothing but my x and y values. Dot df2 transform. df2 transform is nothing but this slopes. When you do this, yesterday you remember you got values, positive and negative values. Here I'm getting all the positive values. There we got positive and negative values. So what this dot operation which you're doing here, between this data points and the slope, you're basically trying to find out how strongly that point pulls the line towards itself. Yesterday we gave it a meaning as distance of the point from the line. Remember that? This is the distance of the point from the line. This also comes from the dot operation. I'm representing my data as a matrix, slope as a matrix. I'm multiplying the two matrices, I'm getting the output. This is not covariance, this is distance of the data point from the line. This operation is also called dot notation. When I multiply two matrices and the resultant matrix is a square matrix, as in this case, square matrix means number of rows is equal to number of columns. Such matrices represent your covariance in the mathematical space. Okay, let's move. These are your data points on the origin mathematical space. Take one data point. It is a combination of xy. This xy is represented as a vector. Vector is basically an arrow from the origin with certain length and certain direction, where direction is given by the angles onto the axis. So all the records in my data frame, I can represent them as n-dimensional vectors. Every record can be represented as n-dimensional vectors. So I take only the numerical part, that becomes my matrix. Okay? So the entire data frame, just take the numerical part, put it in an array, that is my matrix, which represents this data frame. So as many rows, that many rows, as many columns, that many columns. I transpose this matrix. I convert rows into columns and columns into rows. Look at the indices. A11, A12 becomes A11, A12. Why do we need this? We need this only to do a matrix operation called dot operation, where dot operation is nothing but multiplication. Nothing else. What we call multiplication in algebra, we call it dot notation in matrix. So when I do this A dot A transpose, what I get is the covariance matrix. This covariance matrix is nothing but a pair plot. If you look at the covariance matrix here and look at the plot here, diagonally the covariance is all 1. That's why it's all ones. Look at this covariance. This is a negative relationship. As your x increases, the cloud comes down. Negative correlation. You will see a negative correlation. You see a strong positive correlation. You will see a strong positive correlation. So what we call pair panels is your covariance matrix. And we can visually see that the dimensions are not independent of each other. They are influencing each other. That's why you're seeing such linear plots. If two dimensions are independent of each other, you see a sphere, spherical. But given that I'm seeing non-spherical distributions here, that shows that the two dimensions are interacting, influencing with each other. Change in x leads to change in y. What is the degree of influence each dimension has on the other? That is represented in a magnitude term over here. And if I build a model in which I supply the dimension x1, x2, x3, x4, then that algorithm is going to make use of only the variance on x1, variance on x2, variance on x3, variance on x4. The algorithm is not going to get the information that is there in the mathematical space. It's going to make use of only this, 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 this. Right? So it doesn't have any access to the information in the mathematical space. So this matrix, we convert it into, when we do that eigen decomposition of that matrix, mathematically when we convert this eigen decomposition of this, it results in this matrix, where off diagonal everything is 0. Which means these dimensions 1, 2, 3, 4, 5, 6, whatever it is, all these dimensions are independent of each other, and these dimensions are your principal components. And these, what you see here, these are the variances on each one of the principal component respectively. PC1 eigenvalue, PC2 eigenvalue, PC3 eigenvalue. So this is the objective and this is what it achieves. While doing it, the output of this operation is two. One is the diagonal, which is your eigenvalues. The other one is the principal components, which is the rows. Okay. In case you want to further deep dive into mathematics behind it, it's all here. But I'm going to move on to hands-on. It'll be too much for you to get into this without knowing certain properties of matrices. Okay, so I'm going to leave it to you. In case you're interested, you can go through it. Let's get on to some hands-on. Yeah. Look at this covariance matrix. You'll see a relationship with this. Okay, so this is my covariance matrix. This has been transformed into diagonal. In the process, you got the eigenvectors and the eigenvalues. Now let me help you interpret these eigenvectors. You have the original mathematical space, which you centered and you came out with this. Now this vector which you're talking about, it can be represented as an arrow in the mathematical space. This arrow in the mathematical space, in the original non-centered set, or you can take even in this has some value on this dimension, some value on this dimension. These values which you see here are these values which you see here. How many dimensions were there in this particular data set? 4. So you'll have 4 entries for one vector. If it had 2 dimensions, you'll see 2 entries for every vector. So this tells you the position of the vector in the mathematical space. Right? Are you with me, lady? Here you are. Anybody left behind? Okay. See, I'm looking London, seeing Tokyo. I know that. So I'm talking to her, she's nodding her head. I've talked to her, she's nodding her head. All of you with me? Yeah? You're able to understand what is this? This is position of the first eigenvector in the mathematical space. And this eigenvector, it captures this much of variance. This is my eigenvalue 1. Second eigenvector, eigenvalue 2. So on and so forth. These eigenvalues and vectors, usually they'll come in sorted order, but sometimes it might not come in sorted order. You may have to sort it. Alright? That will happen when your data in the mathematical space is not distributed like a rugby ball. It is distributed something like amoeba. Then it may so happen that your eigenvector 1 definitely the max the eigenvalue. Eigenvector 2 might have less than eigenvector 3. It can happen. Okay. Alright. So we got our eigenvectors there. What I'm doing here is I'm going to do what is called cumulative plot. So let me first show you the plot, then it will become easier to understand. I'm trying to plot against each eigenvector 1, 2, 3, 4. How much eigenvalue? This is simple bar chart, nothing else. But this is what the cumulative frequency is. So first eigenvector gives me around 55% of the information in the original mathematical space. The first eigenvector captures around 55% of the variance in the original mathematical space. First 2 eigenvectors put together capture around 80% plus of the information in the original mathematical space. Go to the third one. First 3 eigenvectors cumulative capture around almost 95 to 97% of the information in the original space. All eigenvectors put together capture 100%. Now look at the last eigenvector. the delta information that it captures is only this much, this one. Do you think we need to keep that eigenvector, or can we drop that eigenvector and create a new mathematical space with only 3 eigenvectors? It's your choice. Okay? So this code is for this plot. Nothing algorithm is there. Okay? Coming down, what I'm doing is I'm going to put these eigenvectors and eigenvalues on one single data frame. So I'm creating what is called eigenpairs. You can call it anything you like. So I'm taking the eigenvalues and the eigenvectors. First eigenvalue, first eigenvector, put it in a data frame. Second eigenvalue, second active, put in. So this is a for next loop for that. So now this is my data frame, eigenpairs. First eigenvalue, it's eigenvector. Second eigenvalue, it's eigenvector. Are you all okay? All right. I just noticed I have used absolute function here, which is not required. Because eigenvalues are variances, which are squared term. They will always be positive. Eigenvalues are variance. Variance is a square term, x minus x bar raised to power 2. It will never be negative, right? Anyway, forget it, not very important. Let's come down. So I created this array of eigenvalues and eigenvectors. I'm going to stop here. I want to make sure that all of you are with me. Do you understand what's going on? Are you all with me on this? Guys, this side is very quiet. What happened? Yes. All data points put together define a new set of dimensions. Those dimensions are called eigenvectors, and the distribution of the data points on that eigenvector is called eigenvalues. Since you asked, let me just show this to you on board. I know this can be slightly slippery at times. So if this is my original mathematical space which has been centered after converting a z-scores. So these are all data points. The first eigenvector is the one which connects the two farthest. Right? This is my eigenvector 1. So what we do is, what this algorithm does is it projects all of them onto this. It projects all of them into this dimension. Now you've taken care of this spread. How about this spread? Data spread here also. So we put an orthogonal to this, 90 degrees. All the data points are projected onto this. Once that is done, we don't need these two dimensions. You rotate this. That is what the matrix transpose operation does. So now you have a new set of dimensions where the data points are scattered. You will never be in a situation where there is no relationship at all. It's absolutely zero. That will never happen because of the noise in the original data set. You'll find some spread here, but most of the spread is gone. So between eigenvector 1, eigenvector 2, the covariance will be 0. Between the original dimensions, the covariance was greater than 0. Okay, here I'm using a horizontal stack function of numerical Python and converting this into a two-dimensional array. Okay, now look at this. This is where from eigenpairs, okay, eigenpairs, this is 0, this is 1, 0, 1, 0, 1. From eigenpairs, I'm creating an array of 4, 1. Reshaping into 4, 1 means 4 rows. And eigenpairs reshape into 4, 1, again 4 rows. And okay, why am I doing this 4 into 1? Okay, maybe I wanted to restrict myself to 4 dimensions, that's why 4. But originally we had 4 dimensions, right? Originally we had 4 dimensions. Okay, sorry, mistake. I was confusing myself. I'm converting this into a matrix. Now, how am I going to use this matrix C over here? Originally, my training set was 1097 records, 4 dimensions. Original data which we loaded had 1097 records, 4 dimensions. The 5th one was target. I did a dot operation between that. I did a dot operation with a matrix of 4, 2, where these are 4 eigenvectors and their corresponding eigenvalues. As a result of this, I get a resultant mathematical space now, which has 1097 records but only 2 dimensions. So I'm reducing the number of dimensions from 4 to 2. So when I project this original data into this 2 eigenvectors dimension, the resultant is 1097 records but in 2 eigenvectors. So from 4 dimensions I have reduced to 2 dimensions. Why 2? No reason. I'm just showing you how the dimensional reduction happens. How do we drop it? Yeah. If you want to do dimensional reduction, you need to do this. If you don't want to do this, you don't need to do this. You can continue with 4, 4, right? All right. Now we got our eigenvectors here. Yesterday we did support vector classifiers. We discussed that SVC is one of the most strongest classification mechanisms available, which will use internally its kernels and kernel tricks. So let's see what kind of job it is able to do on this data set. On one hand, I'm feeding it with very rich information. On the other hand, I'm going to make use of a very powerful algorithm. So let's see what kind of results we get. So I import SVC, support vector classifier, train test split. I'm instantiating my support vector classifier here. I'm using the default parameters. So what is the default kernel here? RBF. Default kernel is RBF. Yeah. On that, I'm doing the fit function here. And then I do a scoring over here. Let's see how it does. Keep in mind, scoring is done on the test data, and test data has been independently transformed. Look at the score you're getting. This is kind of, honestly, this is very uncomfortable to me because I had never got a score of 1, which means 100% accuracy on any test set. So this is slightly kind of uncomfortable situation, honestly. Yeah. But maybe it's one of those statistical flukes where, in spite of treating the test data separately, just getting a score of 100% accuracy in classification. This is not on training set, this is on test set. And I'm very confident that my test data has not been seen by this algorithm because we transformed it separately. On the same data, let's apply logistic regression. The standard techniques, on the same data I'm applying logistic regression. Doing my scoring, logistic regression also performs well, but it's giving around 98%, 98.5. Not bad, logistic. On the other hand, look at Gaussian naive Bayes. Supposed to be a very strong algorithm for independent variables. Naive Bayes assumes the variables are independent of each other. PCAs are all independent of each other. But unfortunately, naive Bayes is for some reason performing poorly, even though the independence assumption has been met here. Remember, naive Bayes algorithm, it's called naive because it assumes the dimensions are independent. Here we have used PCA, which are independent, but still it's performing relatively poorly, significantly poorly. Right? And look at this SVC. Shift. The default kernel is RBF. RBF will project your data into infinite dimensions where they will become linearly separable. if you look at the distribution of the data here, most of the dimensions, the distributions are overlapping, but they are not eclipsing each other except for these two cases. So it looks like the Cover's theorem has made them linearly separable in some dimensions. Even if on one dimension they become linearly separable, it's enough for classification. Right? So PCA with support vector machines, logistic, and your naive. Whenever you use naive, you look at your pair panel. In pair panel, if you see linear correlation between the dimensions, always try to compare that with PC dimensions, performance on PC dimensions. So because naive assumes independence between dimensions, applying PCA might give you good results. Shall we begin? Are you all ready? Yes or no? Okay. We still have time. So this is AutoMPG analytics, which I've been talking about since yesterday. I'll quickly tell you what I've done on this. Okay. This AutoMPG, when I came across this data set long time ago, the accuracy of this data set in prediction was somewhere around, if I'm not wrong, 76 to 80%. It will not go beyond that. Are you all familiar with the data set? Okay. It won't go beyond that. But then I noticed in the pair panel, when I do KDE, kernel density estimates, okay, this kernel density estimates clearly shows there are likely to be multiple Gaussians in my data set. So I mixed up data from different Gaussians. I've mixed up data from different processes. When you mix up data from different processes and you're trying to build one single model for all the data set put together, maybe you're doing a mistake. The miles per gallon of a small car will obviously be much higher than the miles per gallon for a large car. But the characteristics of a large car is very different from that of a small car. So do you think it makes sense to build one single model for each one of these segments, or should we build separate models for these segments? Same way, when you do this loan data set, where people have applied for loans for different category of loans, student loan, car loan, house loan, business loan, and we are trying to build a model to predict the defaulters. Do you think it's right to build one single model which predicts the defaulters? Because the characteristics of a defaulter who defaults on business loan will be very different from the characteristics of a defaulter who defaults on student loan. So should you be building one single model which predicts whether it's going to be defaulter or not? The reason why you should not be doing such things is when you have multiple Gaussians and you're treating the entire data set as one single unit, if you're building linear models, say for example, the linear model always goes through the x bar and the y bar. But here, the x bar is going to be represented by something which neither represents this process nor represents this process. So the model which goes through the x bar and y bar will neither represent this properly nor represent that properly. And this has come out in this analysis beautifully. Look at this analysis. I did a k-means clustering on this. This is the linear model we built. You already know this. It gave me around 89. This was using I was using support vector machine. No wonder it's giving me 89%. But when I built simple linear model with lasso and ridge and all these things, it was not going beyond 80%. When I went and did an analysis of this on clustering, why is it not going beyond this range? I found that there are at least 4 clusters in this data set. 4 was a bit surprising because I know small cars, sedans and large cars. But still, when we went ahead and this is clustering, now look at this. Forget all these things. You already know all these things. Interpreting the clusters, instead of interpreting the clusters using your z-scores, the centroids, you can interpret the clusters doing box plot, right? So I'm assuming that you know all these things. Who did that? Oh, it's back. Okay. When I did that, now look at this. This is what I was telling you yesterday. I took cluster-wise, I gave different colors to different clusters, and I took this analysis. Okay, let's see MPG versus horsepower. When I do that MPG versus horsepower using SNS pair plot, cluster-wise, can you tell me what is it telling you? The relationship between horsepower and MPG. By the way, what is this blue data points? Sorry? It's a cluster, but cluster of what? Large cars. Large cars. Horsepower is very high. Green data points are your Maruti 800s. Small cars. Right? And we can very clearly see the relationship between horsepower and MPG for large cars is almost flat. The relationship between horsepower and MPG for sedans is okay, for small cars is okay. So when I build different models for different clusters, for large cars, I may not include horsepower in my model because it's a weak predictor. Whereas I might include horsepower for predicting miles per gallon for small cars. Not only my algorithms might be different, but the dimensions I used for prediction also might be different. That is the advantage of clustering. Clustering tells you all this information when you do that. Okay? And your principal component analysis is tied up with clustering. Please go and explore how principal component analysis and clustering are related. It's almost flat. The slope is almost zero. Yeah? For a very large change in horsepower, your miles per gallon drops by a few amount. So it's a weak predictor. Look at the other case. This is your displacement versus horsepower. It's coming out, same thing is coming out. For large car, displacement versus horsepower is almost flat, not very flat, but look at this one. This is the relationship between acceleration and MPG. What it is telling you is for large cars, very significant difference in acceleration causes a slight drop in your MPG. It's almost flat. The red line is almost flat. Right? And look at the green line. Any questions, any observations on the green line? This is what I was discussing yesterday. So today I thought I'll show it to you how we do that. But right now I'm going to move on. I'm going to go to PCA. Once again, the same data set. All these are standard stuff. I hope the data set is here. It is here, correct? Okay, it is here. Again, you're aware that there are question marks in this data set on horsepower column. I'm replacing all those things with median. Coming straight down. Independent variables and dependent variables. Coming straight down. Don't do this mistake. Always split your data first into training set, test set, then do the standard transformation. What we are doing here is called data leak. I'm going to transform the data set first into z-scores, then I'm going to break this into training set, test set. This is what we call the data leak, where your test data has already been influenced by your training set. In your capstone projects, you shouldn't do this mistake. This will be a killer when you do it and you're caught. You'll not be able to defend. I've left it as it is because I wanted to discuss this point with you, but otherwise you should not be doing this. Are you all okay? You're with me? Shall we move on? Yeah, okay. So then I built again same stuff, covariance matrix. This covariance matrix is nothing but a pair plot. Once I get the covariance matrix, I need to use the eigenfunction on it. to transform this covariance matrix into diagonal matrix. When you do that, the resultant is an eigenvector and eigenvalues. The eigenvectors are again, these are the coordinates. Once again, you can see there are 1, 2, 3, 4, 5, 6, 7 dimensions because you had 7 dimensions here. These are the 7 dimensions, excluding the target, right? Till now, you're okay? Since it outputs these vectors and values in separate arrays, we combine both of them into one single array. We call it eigenpairs. You can call it anything you like. Then eigenpairs, I'm sorting it. When you sort it, by default, it is sorted on the 0th column. That is your eigenvalue column. And I reverse it. Reverse means descending order. I told you the eigenvectors and eigenvalues need not come out in a sorted way. It need not. For example, look at this. 48, 13, 6. Is it coming out in an unsorted way by any chance? No. 0.03, 0.06. Look at the last two. Yeah, last two. Last two are flipped. 0.03 is coming before 0.06. Okay, this will happen when the data is distributed not like a symmetric distribution. It has some kind of weird distributions on some dimensions. Then you might come across this. So we are going to sort it and get in the descending order. When you do that, the topmost one is eigenvector 1, eigenvector 2, 3, 4. There you go. It's sorted in terms of eigenvalues. The eigenvectors and eigenvalues. Once again, I'm doing that cumulative analysis. How much information captured by each eigenvector. So that is coming out like this. And as you can see, the last 3 eigenvectors, very tiny contribution to the overall information. The amount of variance captured by the last 3 eigenvectors is very tiny. So I might drop the last 3 eigenvectors and create a mathematical space of only 4 eigenvectors if I wish. Right? There you go. I am taking from the eigenvector sorted array only 4 eigenvectors, which means I am ignoring the last 3. Then this is the point, the dot operation. Sometimes you will not see this kind of flattening out. You will actually see stairs going to infinity. You will not be able to drop any dimensions. That is what you will observe in PIMA diabetes dataset. I'll show that also to you. We'll see that. It becomes difficult to decide which ones to drop when it doesn't flatten out like this. Here the curve is flattening out. Sometimes the curve goes straight up, like steps. So there, dropping dimensions becomes a challenge.
We are having this original data set there are around 7 independent variables, or there are
Correct.
7 dimensions are there. And after doing the component analysis, we see that last 3 are not adding much value.
Correct.
And when you decide to drop, then we try to fit a 7-dimensional data against a 4, right?
Yes.
How does it really work?
So if I had, suppose, 2 dimensions originally, okay, and these 2 dimensions had correlation like this or covariance like this, yeah. High correlation filter. We apply high correlation filter and want to reduce the dimensions. You are free to delete this one or this one. Essentially what you're doing by that is, if suppose I want to delete, I remove this dimension from my analysis, suppose. So what you're basically doing is, you're taking only this dimension with this much spread. But the cost is, you're going to lose out the information stored in this dimension. Okay? This is on the raw data set when I drop my dimensions. So on the raw data set, I know I have dropped x2. I kept x1. But this is not a right technique to drop dimension because you're going to lose a lot of information here. What we do is we convert this into PCA. In this PCA, PC1, it's a composite of these two dimensions. It has absorbed the information from both these two dimensions and representing it over here. PC2 is again a composite of these two dimensions, which is absorbing this much information. This guy is absorbing this much, this guy is absorbing this much. Now when I transform this, so this is the information contained, this is the information contained on PC1, this is the information contained on PC2, which when you plot it as, it comes like this. So almost 90% of your information is captured over here, plus few percentage is captured over here, which makes 100%. Because the information captured by PC2 is not very significant for me, I drop PC2. But now look at the difference. Though I drop PC2, I am not losing the original information values of these two. It's captured by PC1. Which is not the case when you drop the raw dimensions. Which is not the case when you drop the raw dimensions. I repeat, okay? I'll just quickly repeat this. Since we are talking about fundamentals, we need to be clear on this. I have only two dimensions, horsepower and say, what is another one? What? No, this MPG star displacement. Okay, I noticed that between these two, there is a correlation. I convert into PC dimensions, and PC dimension PC1, which is this one, I'm not centering the data now, PC1, it has this distribution. From here to here, whatever the spread is represented on this. PC2, which is perpendicular to this, captures the rest of the spread, what you see here. Okay, this is my PC2. Now, a given data point here has been represented on this PC1 as well as PC2. All data points here, for example, this one is represented on this PC2 as well as on this PC1. It's projected on both. So that means these projections that you see here, this projection, it includes this data point also. Maybe this data point here and this data point here, these two is the original data point. Now when I drop this PC dimension, because it is very low in spread, I lost some information. But the contribution of the data point to PC1 is still there. Okay, now once you drop the PC dimension, using only this PC dimension, I will never be able to recreate the original data. So if I want to go back from PC to original data, I need all PC dimensions intact. The way I got your question is, okay, can we somehow find out in the distribution of this PC2 how much standard deviations away this particular data point is? How much each data point is contributing to the distribution on PC2? That's what you want to find out, right? So when I drop these data points into PC2, there is a distribution here. What he wants to find out is, can I find out how many standard deviations away on PC2 a given data point is? That is the contribution of that data point to that PC2. The larger the standard deviation, more information it's contributing. Right? That's your question. There definitely has to be a way for this, because this is all standard statistical techniques. But off the cuff, I don't know the answer to this. I'll need to refer to my documents. Yeah. So two homework for me. I'll give you 10.
I have an image.
Yes.
Okay.
Yeah.
So so the image is, all images are comprising of red, green, blue combination.
Yes.
Correct. So let's say I would, and I have an image which is given with these respective values. for each pixel
Yes.
on the image,
Yes.
which gives you a RGB values.
Yes.
And I will have a complete map of that particular image itself. Correct. Now the point is I'll have to split the image, correct, into three parts, which is the R part, the G part, and the B part of the image itself.
Correct.
Now with the PCA, correct. Okay. So now if I split the RGB of the image into three principal components, right, per pixel of the image, correct. I'm doing it per pixel. Per pixel is my bottom line. Right, if I split them into three different parts, correct, and let's assume I compress each of this pixel image using some other algorithm. Let's assume it is outside what we are talking about, correct, and now I have to basically use the same. I have these three independent eigenvectors through which I will have to combine them back to the original image. Right. So let's say I have an image, which is first step is I split them into PCA into three RGB values. Then I apply an algorithm which compresses the image. Then I transmit the image. Then I decompress it. Then I get back my three eigenvectors, right, which are showing even these. And with these three eigenvectors, I can combine and produce, a rotated image, for example, right? I can rotate the image, in different dimensions, right? To give a better picture of that image itself. Correct? So so how do I do this with a PCA model driven by an algorithm following, right? Whichever you choose. Right?
Okay.
That is the question. This is a real-time example, that is being tried out.
Oh yeah, no problem. Okay, I'm just thinking, how do I answer this question? Actually, PCA, principal component analysis, is used to store your various audio image files in a compressed way, right? Sometimes when we do for dimensionality reduction there after using PCA, we call it lossful compression, which means when I transform it back to the original data frame, I might not get exact same picture with same clarity and all those things. I may not get. So PCA used for that. All right, shall we move on? We're almost at the end of it. So where are we? Yeah, we did. I lost my track. This is MPG. Yeah. Okay, we got our eigenvectors and eigenvalues. We sorted this. We have seen, now I remember where we are. So last three eigenvectors for me are useless. They look useless to me. Information content is very low. So what I'm doing here is, I'm taking only 4 eigenvectors from the sorted array. We put all eigenvalues and eigenvectors in an array. We sorted it based on eigenvalues in descending order. I'm taking the top 0 to 4, the first 4 eigenvectors. Are you all with me on this? Okay. Which means I'm reducing the dimensionality from 7 to 4. We are dropping 3. Yeah? So 7 to 4. And this is important. So I'm taking only 4 eigenvectors and P underscore reduce. Underscore reduce means this is my reduced mathematical space. On this mathematical space, I'm projecting all my data sets. This dot operation, you see NP dot dot, this is the same dot matrix operation. Multiplying 2 matrices. One matrix is your data set. The other matrix is your dimensions. I'm multiplying these 2 matrices, and the resultant matrix is your data projected onto the 4 dimensions, 4 principal components. Let me explain this to you on the board. This was my data set, original one. Okay, we found out the principal components on this. This part of projecting the data points onto the principal components, this part is what is happening here. NP dot. Same way, I'm projecting these data points back onto this PC dimension. This projection which we are doing is done by this dot operation. Once all the data points have been converted into corresponding values on PC dimensions, then I don't need this. So now I have my data points on 4 PC dimensions. The original data points are present in 4 PC dimensions. I'm converting that into a data frame, and rest of the story is same. Now I'm going to split this data frame into independent variables, dependent variables. Then I build my, look at this. Training set, test set, projected data. This is my projected data frame. Then I look at the pair panel between them. This is pair panel between your PC dimensions. Why am I showing this? What do you expect in this pair panel? How will you know they will appear as independent? The scatter plot will be spherical. The scatter plot, you will not be able to see any trends. When the scatter plot is spherical, that means R value between these dimensions is 0. Very low, not 0, very low. So you can see that effect of your transformations. Right? Look at this. This is MPG, the target variable, versus the PC dimensions. Okay, between PC dimensions, all the transformations are 0. So all the relationship is gone. But between the MPG and the PC dimensions, what is it telling you? Between MPG and the PC dimensions, what do you see? Between MPG and PC dimensions, only PC 0 seems to be having an impact. So I can build a model with only one dimension, because all other dimensions predictive power is 0. But then don't forget, we have done a very fundamental mistake. The fundamental mistake we have done is we have mixed up Gaussians. We converted one z-score, then broken into a training set, test set. So as long as we do such fundamental mistakes, garbage in, garbage out. Go ahead and build your model on this linear regression model on these dimensions. Your accuracy score comes to nowhere near 80%, which we are getting on the raw dimensions. It's 68, 70%. The reason why it is dropped is exactly what I told you. We have done fundamental mistakes, and look at the relationship between your MPG and this. Principal component analysis, very useful technique, but when misapplied, it will take you to this. Question? When misapplied, it will not give you any returns. It will in fact have a negative impact on your analysis. 69%. Shall we move on to one more example before we wind up? This is the famous dataset which we have. That dataset is a PIMA dataset. Let's see if we can use PC on that and improve the performance. Are you all ready? Yeah? Okay. All this is already familiar with you. You guys are familiar with this, so I'm going to jump straight to the point. Now look at the data distribution of original dimensions. Look at the data distribution of the original dimensions. Okay. First thing you should notice is the plots, diagonal plots. The diagonal plots, they have long tails. If you don't like this, you can convert it to diagonal kind. Player plot, data set. Is equal to KDE, and then plot this. Come on, yeah. Look at the diagonal plots and you will see long tails. When you see long tails, you should not be doing principal component analysis on this. Your PCAs will all be wrong. They'll all be incorrect PC dimensions, okay? Let's go ahead and ignore this and move on. So I'm creating my covariance matrix, which I'm going to decompose here into eigenvectors and eigenvalues. When I do this, I get my eigenvectors and eigenvalues. And when I plot the cumulative frequency, this is what I was telling you. It is not tapering off. You see, the eigenvalues are not tapering off. The steps are all significant information content on every dimension. It's not tapering off. So in this case, when I drop some of the least significant one, I lose a very huge chunk of information. But then you are in this kind of a situation because of incorrect PC dimensions. The principal component itself is incorrect. That's when these things will happen. The reason why principal components is incorrect is there are long tails in your distributions, outliers. So when you do this analysis, when you go ahead and build your models on these PC dimensions, you are not going to see any improvement there. Look at this, I'm keeping all the original PC dimensions. There are 8 original dimensions, I'm taking all the 8 PC dimensions. When you do that and build my model, my performance overall is still the same 77%. PMA diabetes dataset cross tabs, the confusion matrix, overall accuracy was never going beyond 78%. So it continues to be same old 78. Class level accuracy is still worse. For the diabetic class, the class level accuracy is still around 55%, which is like random model. The reason I'm showing this to you is, when you're in situation like this, be careful, you should not be applying your PC dimensions. These situations. Look at this. You should not be using PC dimensions, PCA. Many people project PC dimensions as some kind of a silver bullet to all your problems. Nope. Principal components will fail you in such situations. In fact, it will mislead you completely. One last point. Okay. This question came up in Bangalore, so I just wanted to be very clear on this. Look at this density plot and look at this column here. This column is origin, okay? Origin of the car. How does it have a density plot like this? Origin is a categorical variable where you have 1, 2, 3. 1 is US, 2 is Europe, 3 is Asia. Then how can you have a density distribution like this? What's the question? Okay. What you're seeing here in diagonal is called the KDE, kernel density estimates. It is an estimate of the density distribution in the population, which has been kind of derived using a mathematical function called kernels. Okay, so this is not the distribution of your data in your data set. This is the likely distribution of the data in the population. All right. So what you see here, KDE, kernel density estimates, is an estimate of the likely distribution in the population. It is not the distribution in your data set. Of course, what it does is, it makes use of a mathematical transformation technique upon which it applies the Gaussian transformations. Gaussian is normal distribution, and tries to figure out how the density is distributed. There are 3 categories. All the 3 categories have the same spread, but the heights are different because the frequency with which those data points have been found in your data set is much less than this. If all the 3 types of car, America, Asia and Europe, are in same numbers, frequency is same, then all of them will be equal height. But one of the most beautiful recommendation systems was built by Netflix. It was actually a Kaggle competition in which one of those authors came out with that recommendation system based on singular value decomposition, a matrix decomposition technique, SVD, which is related to PCA. He did not win the competition, but Netflix liked his idea more than the first prize winner idea. So they implemented this technique and further enhanced it. SVD, singular value decomposition. You know, the beauty is Netflix, how it recommends movies to you. You have people, you have movies. He will kill me if he sees that I'm spilling all those things. But I'm so interested in this, I'll just tell you. You have people, you have movies. This is broken into two matrices, people and some factors, and factors, movies. SVD operation does this. And when you multiply these two back, you get almost the same, absolutely same matrix. But it does something more. Suppose these people have watched some of these movies, it'll be a sparse matrix. It'll be a sparse matrix. So this person has watched these movies and is given some ratings here. This particular person watched this movie and given some ratings here. It'll be a sparse matrix, okay? What is the rating he's likely to give here and here? That will be predicted in this for you. So in this matrix, you'll get exactly the same rating as you got there, but it will give you some predicted values for the ratings here. So this sparse matrix will become dense matrix, where all the empty cells will have predicted values, what ratings is likely to give for different movies. And mastering this technique, Netflix recommends movies to people, and their sales went through the roof because of this technique. Yeah. Factors is what is the property of the movie which connects that movie to the person. The property of the movie may be the hero, the heroine, the plot of the movie, whether it's a science fiction, so on and so forth. And here is a person who likes these factors. So the factors are like your principal components, which cannot be interpreted in physical terms. We only have to guess what these factors could be. Now that we have discussed the concepts behind k-means clustering, let us see a small example how we implement it in Python. The situation that I'm going to show you now is about a technical support datasets. Imagine you're working as a data scientist in one of the companies, in an IT company, and you have a huge amount of technical support data with you based on the past reports, past incidences reported by the customer. Now your management wants to look at this dataset, employ your skills in data science, and help them improve the CSAT rating, the customer satisfaction rating. So look at the problem statement. The problem statement is pretty ambiguous. You have a data set with you. The management has given you a very vague problem requirement. Can you, looking at the data set, use your data science skills and help them to improve the customer satisfaction ratings? Often in real world, when you do your data science projects, you will find yourselves in similar situation where you have data with you and a problem statement, and somehow you have to now start moving. Very rare will be the case where you will have a data set with well-defined independent attributes, a well-defined target variable, and you are supposed to find the relationship between the target and the independent variables and express it as a model. Not that these kind of projects don't happen, but more frequently, more often, the kind of projects we get into are the ones which I'm going to show you now. So the objective is, given the data set, can we find some useful information hidden in the data set? Using that useful information, we have to improve our CSAT rating. We have to come out and suggest some strategies to our management on how they can improve their CSAT ratings. So let's go ahead and see the code, how it works, how we implement k-means clustering in Python. What you see in front of you is the standard libraries which we import. The pandas, the numpy, the matplotlib. From scikit-learn clustering algorithms, I'm importing k-means. the k-means class. And I'm going to read a file called techsupportdata.csv. This is the historical technical support dataset that we have. When I look at this data, when I load this data and look at the data types, these are the data types I have in my dataset. Problem type is a text, which is of the type object, and rest of the data are all numerical data sets. Some of them are integers, some of them are float. Remember, for clustering, we need all our dimensions to be numericals. In this case, all of them are numericals except for the problem type. Now that we've seen the data types, let's see how the data looks. For that, I do a head on the data frame, and it shows me a sample of 5 records. The first column is your problem type. Temperature control not working, power cord not fitting in, fan swing not working, so on and so forth. These are all the different types of problem statements. How many such problem statements reported in the last unit of time? Unit of time could be month, 6 months, or 1 year. How many calls on an average pending? What is the average resolution time of these calls? How frequently they recur? And how many of them require replacement? How many of them occur with what frequency within the warranty period and outside the warranty period? So these are some details that have been captured from the past technical support calls. So let us see if we can extract something useful out of this. As I mentioned earlier, all the dimensions are numerical dimensions. We have to scale them because we don't know what the units are, and whatever the units may be, we have to ensure that all the dimensions are on the right scale, comparable scales. Recall my example on the discussion about the 3 people, 2 with slightly different heights and different weights, and 1 with 6-footer who had same weight. So what I'm doing here is, I'm making use of the z-score function, which I'm going to apply on all the columns and convert them into corresponding z-score values. However, one of the columns, the first column, the problem type, it is a non-numerical column. A z-score will not work on it. It will give you an error. Hence, what I'm doing here is, I'm making use of this drop function, which is available in Pandas data frame. So on the data frame in which I have loaded the dataset, I'm calling this function drop. You have to specify what to drop. I want to drop this column called problem type. Access is equal to 1 or access is equal to 0 are the 2 options available. Since we're going to drop a column here, I'm going to use access is equal to 1. When I do that, from this table or this data frame, that particular column is removed, and rest of the columns which you have, they are captured in this new data frame. Just for information's sake, for people who are coming into this coding for the first time, at this point, now you're calling this function drop to remove this column from this data frame. The original data frame tech_support_df will remain intact. It will not get the column problem type will remain intact. It will not be removed. What's going to happen at this line is, all the columns except for this column is going to be copied into this new data frame called numeric columns. You can name it anything you like. I'm calling it numeric columns because all the columns there are numerical in nature. Now on this numerical column, sorry, I repeat that. Once again, from tech support df, I'm popping out the problem type, the column called problem type. Pop actually deletes, physically removes the column from the data frame. Drop does not, pop does. So I'm capturing the problem type and storing in a separate array called prop type. So at this point, what I've done is I've segregated the numerical and non-numerical columns. On the numerical columns, I apply my z-score function. At this point, all the values in the numerical columns, they become z-scores. So I'm capturing those values back in the numerical columns data frame. And here, watch this carefully. Numerical columns dot join problem type. I'm recombining the numerical columns with the label column, the problem type column. So when I recombine these two, now my data frame, if you look at this text support df now, when you run this, you will see that all the numerical columns, their values have become z-scores. And since I appended the problem type in the end, the problem type has been moved to the last. Compare this with the original data frame where problem type was the first column and the data were all numerical, integral values. It does not matter whether you have the problem type as first column or the last column, it doesn't matter. So in short, what I've done is, from the original data frame which is right now in front of us, I've separated out the numerical columns, I've separated out the non-numerical columns. The numerical columns are converted into z-score and recombined these two columns. That's all I have done till now. As I said, now we need to find out if we can apply k-means clustering on this and give some meaning to those clusters. But then how many clusters should I look for? What should the value of k be? One way of doing that is the elbow method. The other way of doing that is the numerical analysis. So I'm making use of Seaborn libraries here. And I'm making use of the pair plot function in Seaborn library to draw the plot on the numerical columns. And the diagonal, I want them to be density curve, density estimates. When you do this and you look at the plot, in this entire pair plot, what is most important to us right now is the diagonal. Look at the diagonal. If you observe the diagonal carefully, the very first plot, if you see, you can easily see there are at least two. One, and there's one behind this. Two Gaussians overlapping. Look at the next column. In the next column, if you observe carefully, looks like there are three Gaussians here. One is a small one and two Gaussians overlapping here. If we had a categorical column here, and if we could give the color to the categorical columns, then we could clearly see the curves overlapping. I'll show this to you in the next example. Look at this dimension. This is dimension on resolution time. You can clearly see two overlapping curves. We call them the Gaussians, two overlapping Gaussians. So right now the maximum number of Gaussians which we think we can see are 3. 2 of them are coming out clearly here. Let's move on. So when you do this analysis, you see this is my recurrence frequency. This is recurrence frequency. Recurrence frequency is also showing 2. Come down, and we see multiple peaks and valleys here. This happens to be a replacement percentage. This is my replacement percentage, and in replacement percentage we at least have 2, and the other 2 are very small, minor kind of Gaussians, may not be very reliable. Similarly, if you look at the other dimensions, you can see that most of the dimensions, 2 Gaussians definitely stand out. One dimension we can see a pale shadow of a third Gaussian. Maybe there are Gaussians in the range of 3 to 4 or 3 to 5, something of that sort. Since most of the dimensions are showing us 2 Gaussians, Let's go ahead and build a k-means clustering here. And let's build the k-means clustering starting with 2 Gaussians. But before I do that, we found out through visual analysis that we could have 2, 3, or maybe slightly more than 3 also Gaussians. Now that we have seen multiple Gaussians on individual dimension, in one Gaussian we could see a pale shadow of one behind the other, and total number of Gaussians looks to be 3, and in other cases they look to be 2. We can look at a range of 3 to 6 Gaussians. What do you mean by this? Imagine the dimension on one of the dimensions that you saw. You're able to see 3 Gaussians where one Gaussian is hidden behind the other, and so on and so forth. When I look at another dimension, in that dimension I'm seeing 2 clear Gaussians. When I combine these two, maybe your Gaussians are distributed somewhat like this. You are seeing a Gaussian here, you're seeing a minor Gaussian here, and then you're seeing one more here. Or maybe, sorry, one more here. I'm going to erase this. Imagine this is not there. So when I look at it from this angle, I'm seeing one Gaussian here, one minor Gaussian hidden behind this, and the other Gaussian here. This one gives you this one gives you this one gives you this. Whereas when I look at from the other dimension, I'm seeing one Gaussian here and one Gaussian here, where these two get eclipsed. So the number of Gaussians could be 3 at least, or it can be more than 3. Maybe there are 2 Gaussians here and they are overlapping, but we are seeing it only as 1. So the visual analysis gives you an idea about how many to look for. Right now it looks like we are looking at 3 minimum, and it could be more than 3. The best is to multiply 3 into the other dimensions. Most of the other dimensions are showing 2 Gaussians, so 3 into 2 is 6. So we'll look for in the range of 3 to 6. Let's go back and employ the elbow method and see how many Gaussians are what is the k value we get from the elbow method. So once again, from my data frame, I'm dropping the problem type because it's an object type column. I'm keeping only the numerical variables in which I have to find the Gaussians. I've written a small for next loop here, and for this for next loop I'm going to supply clusters in the range of 1 to 10. What it means is I'm asking this algorithm to try out k is equal to 1, k is equal to 2, k is equal to 3, k is equal to 4, up till k is equal to 10. For every iteration where it takes one particular value of k, plot the sum of squared errors. And let us see how the plot looks. So this for next loop, if you look at it carefully, for k in clusters, what it means is for k in this range 1 to 10. So the first time the value of k will be 1. Call the k-means algorithm and set the number of clusters to that much value. So first time when you run it, number of clusters n underscore cluster will be 1. Then it will come out with the sum of squared errors, which I'm capturing in an array. And the array is called mean distortion, so you can call it anything you like. Then in the next iteration, the value of k will become 2. The k-means will be called, and it will be asked to look for 2 clusters. It will find those 2 clusters and it will capture the sum of squared errors and store it in this array, mean distortions. Once you've done that, it'll come to the plot statement, where in the plot statement all I'm doing is plot the k values against the mean distortion or the sum of squared errors. As you can see, the error is highest when you have 1 cluster. It steeply falls for 2 clusters. It further steeply falls for 3 clusters. 4 cluster also the fall is relatively steeper. But the 5th cluster onwards, look at the 5th cluster, the fall is not steep. What do you mean by this? Look at the distance between. Let me explain this to you on a PPT. Let's look at the graph that we got in that sum of squared errors versus number of clusters. So number of clusters increased from k is equal to 1 here up till 10. This is my sum of squared errors, or what we call the inertia. Inertia is going down. Look at the first cluster when k is equal to 1 and k is equal to 2. This dy by dx, look at this dy, drop in errors for one small change, 1 unit change in number of clusters, dx. Look at this drop. This drop for the first step from cluster number 1 to cluster number 2, dy by dx, is comparable to the dy by dx from 2 to 3. So this is 1 cluster, 2 clusters, 3 clusters. So when I move from 1 to 2, there's a drop. When I move from 2 to 3, there's a again significant drop. When I go from 3 to 4, the drop is still high. For 1 unit change in number of clusters, the drop is still high. However, after 4, if you look at it, from 4 when I make it 5 clusters, the drop in sum of squared errors is reducing. So from 5 when I go to 6, it reduces further. The drop in sum of squared errors reduces further. Or in other words, the magnitude of the drop with every increment in the number of clusters, somewhere around after 4 clusters, the magnitude of the drop in error decreases. Maybe the optimum number of clusters is 4 or 3. And this is what came out in your visual analysis also. In visual analysis, there was one dimension in which we saw 3 clusters, and most of the other dimensions we saw 2 clusters. 3 into 2 is 6. So our optimal k value has to lie between 3 and 6. So let's go and see whether it is 3 or 4 or 5 or 6. Since most of the dimensions showed 2 clusters, let's begin with 2. So here I'm going to recreate my k-means clusters. I'm reinstantiating the k-means algorithm. This time I'm asking you to find 2 clusters. K is equal to 2. This is the k-means object right now which we have created. On this object, we fit the given tech support numerical columns. Now this is where I would like to caution you a bit. In k-means clustering, you will come across function like fit and predict. But keep in mind, we are in unsupervised methods. We have not built any models. So the fit and the predict that you come across in this is not like the fit and predict that we use in supervised methods. So when I call this function fit and I supply my attributes to it, this is the point where all the centroids, the random 2 centroids are generated, then all the data points from the random 2 centroids are found, how far they are, they get associated with the 2 centroids, the centroids move in the mathematical space. All these things happen at this point. Finally, hopefully, the centroids will settle down. It will not end up in an infinite loop calling for a hard break. Hopefully, it will settle down. And then, once the centroid are found, I make use of the predict function, to which again I supply the same data set. Why am I doing this? When you do this, every record in your data set will get associated with one of these centroids. So the centroid label will be captured along with every record. So if my data set has 1000 records, for every record starting with the first to 1000, it'll sequentially allocate the centroids or the groups to which that record belongs. So this array called prediction will have 1000 entries. First entry for the first record, second entry for the second record, so on and so forth. And in this array, we'll note down the first record belongs to this centroid, second record belongs to that centroid, so on and so forth. Once this is found, what I do is, in my original data frame text underscore support underscore df, I add a new column called group. You can call it anything you like, to which I am sending the information from the prediction array. So whatever you captured in the prediction array will now be copied into this. So let's go and see how it looks. So we're going to run k-means clustering on 2 clusters. Okay, looks like I have not executed one of the previous steps, so let me go back and re-execute the previous steps. There we go. And come back to this. Okay, there you are. Now look at the data set. What I've done here is, instead of printing the entire data set, I've just taken 2 columns, the problem type and the group to which it belongs. In case this is causing confusion, then what you can do is tech underscore support underscore df dot head. Look at this. This is a z-scored data frame. Look at the last column. The last column is the group column, which was not there earlier. This got added after we created the clusters. Since k is equal to 2, the only values you will find here is 0 and 1. What I wish to do is, I wish to show you the problem types and which group they belong to. So temperature control not working, power cord not rightly fitting in, fan swing not working, all these belong to cluster 1, whereas all the other things belong to cluster 0. Let's see if we can extract some useful information out of this clustering. Okay. I repeat. Now that we have seen the problem types and the groups to which the problem types belong, let's see if we can extract some useful information out of it. To extract the useful information out of this, what I'm doing here is, I'm making use of a function called boxplot. I'm assuming all of you know what boxplot is. To this function, I'm supplying the tech support df. So every column in tech support df will now get a boxplot. But within the boxplot function, we have used a command called by. By means do it group wise. So there are 2 groups. Every column there will be 2 box plots, one for group 0, one for group 1. When you execute this line, this is the box plots you get. Look at the first column, average pending calls. The box plot of the 0th cluster and the box plot of the first cluster. What it indicates to you is 0th cluster consists of those kind of tickets whose average pending calls, the value of average pending call dimensions is very high. Related to that, cluster 1 consists of those tickets whose average pending call values on the lower side. Look at the resolution time. Cluster 0 consists of those tickets whose average resolution time is relatively very high. What you see on the vertical axis is the z-scored value. So compared to this cluster, the average resolution time of this cluster is very high. Average resolution time of this cluster is very low. Look at the third one, in warranty period. Cluster 0 consists of all those tickets whose in-warranty period is relatively higher. But cluster 1 consists of those tickets whose in warranty complaints, they range from a very small value to a very large value. There's significant range. Same way with warranty percentage, replace percent, number of cases. This is interesting. Look at the number of cases here. Cluster 1, that is the second cluster. This is cluster 0, cluster 1. It's given on the x-axis. The second cluster consists of tickets whose number of cases, that is number of open cases, is very high. I'm sorry, I take that back. Whose number of cases reported is very high. Compared to that, number of cases reported in the 0th cluster is very low. Look at this dimension, and this dimension you analyze in the context of this dimension, average resolution time. Even though the number of cases reported is very high, the resolution time is very low. Number of cases reported is very low, resolution time is very high. So this clustering is telling you something. But before we get into that, these dots which you see here, these dots are outliers. And as I discussed with you while discussing the concepts, outliers can make your clusters completely meaningless. So let's go ahead and do something about this. Instead of 2 clusters, let's see what happens when you do k is equal to 3. So I'm going to repeat all the steps, and this time I'm going to start with k is equal to 3. In k is equal to 3, now you look at the box plots. You can ignore these comment lines. Look at the box plots. When you draw the box plots, something very interesting is coming out now. Cluster 0, cluster 1, cluster 2. Average pending calls, average open calls for cluster 0 is very low. There are outliers. Average pending calls for cluster 1 is very high. Cluster 2 is very low. Average resolution time for the 0th cluster is very low, so is it for the second cluster. It's very high for the in between, the cluster 1. Let us look at the number of cases. The number of cases for cluster 0 is the highest. That is, number of times this problem is reported by customers is the highest, but the resolution time is very low. On the other hand, the second cluster consists of those cases where number of cases reported is very low, but resolution time is very high, and pending is also very high. They take a lot of time to resolve. What is it telling you? Take your time and try to understand what this box plot is telling you. These 3 clusters are telling you something. What these box plots are telling you is probably the cluster 0, where the number of cases reported is very high, but the resolution time is very low. It consists of those problems which we call the teething problems. When your customers take your products and services for the first time and they come across these very minor issues, they report all these issues to you. That's why your number of cases is very high. But these cases get resolved in a fraction of a second. Some nut being loose or something not right, those kind of things. On the other hand, if you look at the next cluster where the number of cases is low, but resolution time is very high and pending calls are very high. They've been pending for quite a long time. These could be those problems which require technical help, they require technical expertise to solve these problems. Could be a motherboard failure, or could be some other internal hardware failure which requires the product to go to the factory. That is why the average pending calls is high, resolution time is also high, even though the number of cases reported is low. Similarly, the third cluster, the number of cases reported is significantly higher compared to the second cluster. The resolution time again is small, and the pending calls is also small, but not as small as the first cluster. Maybe these are some kind of issues which require some kind of a design change, some kind of a training, those kind of things, training for the customer. So what is coming out of this is, since you started all this analysis based on your management's request to dive into the data set, use your knowledge of data science and suggest something to improve the CSAT ratings, what I would do in such cases, I would go back to the management and advise them to ship a self-help manual with all the products and services so that these teething issues can be resolved by the customers themselves. They don't have to report it. Since they don't have to report it, they don't have to wait for a resolution. Probably they'll be much more happier than waiting for somebody to come and resolve it for them. These problem statements in the second cluster, since they have been open for quite a long time and the resolution time is also high, maybe they need some kind of process improvement, some kind of trainings for the teams so that they bring down both the resolution time and the pending calls. Similar is my analysis for the third cluster also. So we go back to the management with suggestions for each cluster, and hopefully the management will implement these suggestions, and over time the CSAT ratings will improve. So what I've demonstrated in this example is how we can make use of a technique called k-means clustering, dive into the dataset, and extract some meaningful information out of the dataset that can be used to implement your strategies. I hope you understand how we make use of k-means clustering. There is much more depth to it than what you have seen here. Hope you will go and explore those other details about k-means clustering and master this technique. As I said earlier, this belongs to the EDA, exploratory data analytics stage, and it's a very useful tool if you know how to implement it correctly.
So yesterday we actually looked at k-means and we used it for customer segmentation, right? That was one of the biggest use cases for k-means. So before we start, any questions there? Or maybe just to quickly revise, what are the different distances methods that we discussed? And what are the different Euclidean methods are there? One is the regular Euclidean, then you have squared Euclidean, and then you have the L1 norm or other Manhattan approach, right? And then other than this, what approach? Cosine similarity, right? And Jacquard, basically Jacquard index we used, and added distance. Yeah, that was a little funny, but apparently it's a thing, right? And what else did we discuss? We talked about how to use confusion matrix with the categorical data, right? And in terms of, so that was the way to calculate distances between any two data points. We also talked about calculating distances between clusters. So what was the different approaches, if you remember, for clusters? Right, centroid was one because we used it. Centroid. And second was, maybe just minimum, which was the minimum distance between any 2 points in two clusters. Then which was also called single linkage. And then we had the maximum opposite of it, right? And I think it was called complete. And then, of course, average, right? Average linkage, right? And then we looked at k-means So what is the goal of k-means? What is the mathematical goal for k-means? Yes, it basically builds the cluster, but the goal, how it builds the cluster is basically it's looking at reducing the SSE, right? That's sum of squared errors. So there are, as I said, WCSS also you will see within cluster squared, sum of squared errors. And then we looked at customer segmentation, how we will do the feature engineering, and finally build a model there, right? I mean, we were able to build a fairly decent model, and I did promise a 3D view. I'm yet to get to it because I had to kind of take a class of my son also. He did some goof off yesterday, so I ended up spending some time. But what I will do over next couple of days, I'll update this notebook and ask Mohini to update all of you. So you will get the 3D visualization also for this one. All right. And same is true with I think you had a question about the association and unsupervised. So that is still outstanding. All right. So we have used k-means on structured data, right? I mean, we saw what we had was a structured data where you have the invoices and quantity purchased and all that. So those were structured data, right? I mean, usually you have these available in your tables, RDBMS tables usually, right? You apply SQLs and all that. So structured data, but that's not the only type of data. I mean, in fact, if I draw, I'm rubbing it off. So let's understand. Okay, suppose this circle represents all kind of data in the world. Okay, double circle. But okay, this circle represents all the data, right? So in this, about 10% of the data is structured data. What is structured data? Data which you can query on, right? You can send a query and and try to understand it, right? It's available usually in tables. This is structured data. Now, 20% of the data is unstructured. So what is unstructured data? Audio, video, social media messages, SMS, somebody said images, videos, email documents, all the knowledge documents we create in offices and then nobody reads them, right? All those are unstructured data. Basically, you cannot query them. You have to read them to really get some meaning out of it. You have to spend effort. So that leaves the question, so what is remaining? 70% is still remaining. What is this 70% data? It is not semi-structured. I mean, that's not the... So what is that 70% of the data? So we talked about 10% is structured and 20% is unstructured. So what goes with structured? I mean, so what is left? Sorry? Mix of both? Not truly. I mean, this is again, sorry? Not pictorial data is unstructured, basically images and all. I mean, pictures you mean, right? Pictorial, yeah. Images are unstructured data. And we have lots of that. What else is remaining? This is a study not by me, of course. I read it somewhere and found it interesting. So I thought, let me, kind of ask you guys what. So what is that 70% data that we are not able to classify here? So 70% data is the data which has not yet entered computers. Basically, it's usually with humans. It's in human brain. I mean, you have a lot of data. I mean, not everybody uses computers or not everything is put in computers. It could be not necessarily, but this is basically with humans. This information is available with humans, but not documented. So it's not accessible to us in any way. I mean, you have to interact with that person to get to know what they know, right? So that's, I mean, that's tremendous amount of data out there, which we will need to harness over a period, and hopefully, we will. But that's just a kind of aside. So today what we are going to do, we're going to start with, please come. We did structured data yesterday, a k-means on structured data. Now what we are going to do is apply, k-means on unstructured data. So there are two key categories of unstructured data. What are those two key categories? Usually we basically classify unstructured data in two categories. What are those? Again, this is not a trick question, but don't worry, it's a simple one. One is the visual data, right? Visual data. So that's like what the vision part, right? The vision part is that's visual. That's one type of structured data, visual data. Another is, the second part is language data, right? Natural language data, the way we speak, the way we read things, how, books and all that. I mean, emails, everything, all that involves language, right? So you have vision, you have language, right? Those two type of data. So that's why you have this, usually you will hear in, AI field a vision or NLP, right? Those are basically, we use these two senses, to see things and to understand a language. We use these powers within us to basically get better, right? These are the powers which we are trying to give to machines. Structured data, yes, we understand quite a bit of it. We know what quantity means, we know what price means and all that, and we are basically have a way to do some feature engineering there. And then we can, feed it to the model. But it's very hard to do feature engineering with unstructured data, because there are just way too many rules. There's way too many rules that's one way of saying that we don't know the rules, right? There's way too many rules. So what we're going to do today is we're going to basically start applying k-means on unstructured data. So for example, we will start with the visual data, images. For example, as I said, if yesterday we were talking about, you have a lot of pictures and say from, a hospital, which may show tumor, right? Or the stage of the tumor, and you have millions and millions of those pictures. So I want to kind of cluster those pictures and see if k-means can find whether, what it can categorize pictures based on the stages of the, tumor, or, maybe like based on the genders and all that, the different combinations are there, right? So we, of course, do not have that tumor data with us, the pictures with us, right? But what we can do, we can still apply, we can try to see how k-means can be applied on images. And one easily available images data set is this one. Everybody's familiar with this data set? What is this called? No, it's not image of numbers. No, nothing like that. So these are real images. Each of them are individual images, handwritten digits, and the data set name is MNIST. MNIST, Mixed National Institute of Standards and Technology. Again, nobody knows the acronym. It's written over there, but it's MNIST dataset, and you will use it quite often because it's a small dataset, so you can try out things on your CPU without the need for a GPU. And this dataset was released by a gentleman named Jan-Lee Kuhn. So and he's one of the prominent name in the field of AI. How many of you have heard of Jan-Lee Kuhn? Nobody? Okay. So, but these are the guys who, because of which we are actually here, right? We are reading, we want to learn AI. So Jan-Lee Kuhn is currently the head of, AI research at Facebook. a very prominent guy along with Jeffrey Hinton, who was thought to be a father, who's taken as a father of deep learning. So Yanli Kuhn actually released this data set long back, and so we are going to use this. We are going to use this data set. So what we have here is we have individual images of digits. 0, 1, 2, 3, 4, 5, 6. Again, all of those. It's very hard to actually build a program without machine learning in this case as well, right? Everybody writes 1, 2, 3 in its own way, right? You can see, this is also 1, this is 1, and this is also apparently 1. I don't know how somebody can write this way. But we can criticize, but, we can... So what kind of human accuracy will be there on this data set? 99, more than 99? Right? It should be the case, but there might be few, digits written by doctors, old doctors, especially. It's hard to understand what they're writing. So, but we should have, and the best possible, accuracy that has been achieved by a deep learning model is around 99.7% on this data set. Right? So we are pretty close to what humans can do. So what we will do, we will use this data set. Why? One thing is the images are very small, so data set is not very big, and the second is it's easily available, right? It's easily available. That's another thing. We need data, right? So but you can try out these examples on any of the. So thing is, in this case, this MNIST data set is not. It's not that you need to use k-means, right? We know. This data set is labeled. This data set is labeled, basically means each image has a label. So what we are going to do is just to try it out with k-means, we are not going to use labels and see if k-means can still figure it out what kind of images are they. If sometimes, because sometimes it becomes very difficult to know what cluster got created. Right, as we were discussing yesterday, once it creates a cluster, we may need to consult with the domain experts to understand, does this cluster make any sense to you, right? But in this case, because we have the labels and we know how 1, 2, 3 looks like, we are the domain experts, so we need not worry about going to the domain experts. So we will use that, and so now the data set is clear. So what we want to do, so what is an image? How does an image looks like to a computer? Pixels, right? Do you want to see how a computer looks at image? Right? It's not 0, 1. Not this. So this is a picture, say for example. What is that picture? What is that digit? If you look maybe you go a little back, I think it will look like 8. Right? I know sometimes, right? This is 8 basically, and you see what this is what it appears to us, 8, but actually these are pixels with values between 0 and 255. Usually that's the, these are grayscale, black and white pictures essentially. So you do not have RGB 3 channels. Usually if you have colored pictures, you will have 3 set of pixels. 3 set of pixels, or rather, 3 set of numbers to represent each pixel. So we are going to basically use, so we have the data, and what we will do, we will try to see how k-means can try identifying different type of images in a data set. So, and we can then apply the same approach where we may not even have labels, right? Here we have the labels, so we can verify the results. But you can use the same approach as we discussed on images where we do not have label. All right. So let's go ahead with this. So, all right. So we will first start with we want to load the data, and so I think the data is already there in the but you can download MNIST in multiple ways. So there is a way to download the dataset using scikit-learn library itself, but somehow it was giving an issue to me. Somehow the site was down or whatever the case may be. So I had to actually install this package called Python-MNIST. So if you want to install that, you can install that as well. And then basically download these two files, which is images as well as the labels. Again, we need not have the labels, but we are going to just compare those things. And so this MNIST package is basically to read MNIST data only. All right. Okay. So what we will do, I have already downloaded these two files, and so I'm not going to execute that again. What I will do, I will go ahead and load the data, and it may take few seconds. Okay, it's done, and I will then convert those images and labels into the NumPy arrays, right? So, and once we are done with that, then we can check shape of the images, right? What information we will get from image shape? So, how many examples are there? How many examples are there? 60,000, right? 60,000. And each example has how many features? So 784, how can an image have just one dimension? Right? Image usually have either 2 or 3 dimension. 2 is like for black and white, and 3 for a colored image. Like here we saw. Here we are seeing there, right? So this is at one, the data in this case, is it 1 dimension or 2 dimension? Right? It has rows and it has columns, right? It should be 2-dimensional, right? It should be 2-dimensional because this is black and white. Now, in this case, I don't know if you can count, but how many rows and how many columns do we have? All right, I think it's hard to count, but these are actually 28 by 28 pictures. 28 rows, 28 columns. 28 rows, 28 columns. So very, very small pictures. Usually, and what is the size of pictures we take from our cameras? I mean, you have a lot of pixels, maybe 2000 by 2000 pixels or whatever, right? I mean, you have a lot of pixels. So these are very, very small pictures. 28 by 28 pixels. So that's why the data set is small and you can still work with on the CPU. So it should be 2-dimensional, but the data we have is 1 dimension for each example. 60,000, 784. That's what we saw, right? The shape of the data. The shape of the data is 60,784. So 60,000, of course, is the number of images, and each image has 784 values. So what does 784 value correspond to? Sorry? These are pixels. These are definitely pixel values. These are pixel values, and maybe we can see some of them. Maybe they are, let's see. Maybe we will check out the first example. You see the pixel values? Right? A lot of zeros, basically blank spaces, and some values between 0 and 255. Right? So that's so there are definitely pixels, but how come we are getting 784? Any thought there? Right. So it is actually 28 by 28. So that all the pixels have been arranged in a single dimension. We can always rearrange it. We can rearrange it, but and we will do that. We'll try to do that. So let's try to visualize how the data looks like. Labels, okay. Labels contain basically for each image. Label has the information on what this image is, what number is this image is. So we might have I'm actually going to use the labels array and just tell give what is that image. Okay, so let's so what we are doing to visualize, we are using matplotlib. Everybody is comfortable with matplot, right? And so we are basically, what we are doing is we are just generating a random number from the total images. So any number between 0 and 60,000, right? That's what we are generating because we want, and then I am basically getting that that particular example from this images array and reshaping it to be 28 by 28. because to display an image, I need at least two-dimensional data, right? And then X's are off, and I'm then printing the label also for that image. The image number is same between images array and labels array. So they are the same corresponding values. So let's try to execute it. Okay, I have not executed the matplot. Okay, it says label 9, and does this look like a 9 picture? Right? Okay. Yeah, I mean, we can display different pictures. I mean, label 3, 9, 7, 4, 5. I mean, there are a lot of pictures we can keep on displaying. So, I mean, that's what our data is. And if I actually remove this part, X is off, then you can actually see it is indeed 28 by 28 pixel. You can see that, right? Like 28 on the in rows and 28 columns. So we can, so I'm not lying. All right. Okay. So we have these images, and we are not really going to make use of labels for k-means, right? So now k-means can be slow. In our last example, how many rows did we work with in our data when we looked at customer segmentation? About 5 lakh, but ultimately, that's right, about 5 lakh, over 5 lakh, and we reduced it, and it became, I think, around 340,000 or something rows. But how many rows the k-means had to look at? 3,900 something, right? About 4,000 rows only. And it was very fast. It was like very quick, right? But if we try to use k-means on larger data set, it can be slow, right? It can be slow. For example, here we have 60,000 images with 784 features. How many features did we use with customer segmentation? RFM, only 3 of them. But here we have to use 784 features, which could be a pain for the this thing. So it can be slow. So what we are going to do is we are going to just take only 5% of the data. What we're going to do is out of 60,000, only 5% images we will take, so that we can do this exercise in the class rather than keep staring at the screen where k-means is running. Right? So I'm just doing the train test split. So everybody, I'm sure you're familiar with train test split. So, and we are basically making test size as 95%. So I can just keep 5% for training. And I will not look at test. Because we're going to run it only on training data. All right, so let's go ahead and do that. Okay. All right. And so now our training data should have only how many example it should have? 3,000 only, right? 3,000 basically. That's what we have. 5% of 60,000 is 3,000, and we can see, what are the actually values in our data set. I mean, what kind of pictures do we have? So we are going to use the train Y. Train Y is nothing but the label information. The train Y is the label information. We can see how many of these 3,000 pictures are 0, 1, 2, or 3, right? So we can basically, it says it's quite fairly even distribution, about 300 pictures of each of the digits. 0, 1, 2, 5 seems to be a little less, but 8 seems to be a little more. But that's the only kind of thing. Otherwise, everything is very, very close to 300, right? So that's our data. Now, what we want to do is apply train model. Apply k-means on it. So how many clusters should we have? 9, 10. In this case, we know, right? In this case, we know, we want to look at, if it can learn those 10 different type of images, right? We know that, right? But again, so we can go with 10 to start with, right? So let's go ahead and see So in this case, I'm going to measure the time also. So what I'm doing is I'm setting up the cluster to 10 and random stat 42. Start time, I'm just measuring how much time it takes and then displaying the time taken by the k-means. All right, so let's go ahead and run it. So it may take, so it is little, we can already see it is slower than, so it took about 5.6 seconds. About 5.6 seconds only with 3,000 images. So if I try to run on 60,000, it'll take probably a few minutes. All right. So 5.6 seconds was taken, and then we can check. We can see that it has 10 clusters. You can get the cluster information with this property of cluster underscore centers. So it has 10 clusters, and each cluster has how many features? 784. So cluster is also a point, is an image basically. You can see the cluster is also an image because each data point in this case is basically each example is an image. Even the cluster is an image, right? Everybody agrees that? And we can, if you want to look at the SSE, which is sum of squared error, we can see that, oh, it's a massive number. It's hard to make out of it. 754 million something. So there's a big kind of a SSE in this case. But this is a relative number, right? So what we can do, we can see, what we want to do now is we can look at the centroid, the picture of the centroid to see what kind of pictures are they. Because the centroid kind of represents the mean of all the points in that cluster. Right? So let's see how the centroid looks like. So what we are doing is we are basically first of all getting how many centroids are there, and then we are going to display those images in a subplot. So we are going to have 10 subplots, right? And you can have subplots in matplotlib, and then we are going to use this plot imshow, and then we will do exactly what we did earlier, where we displayed different pictures. But now we were going to display 10 centroids. So what is the mean of all those points in a cluster? So let's go ahead and do that. And so this is what it comes up with. We did not give it the labels. If you see, we did not give it any label, right? We just fed the train X, which is the images. So there is no labels fed here, but still it is actually able to see that one cluster is actually belongs to 2, another one. It could, because, so yes, and this is a good example to take. So the thing is, k-means is not perfect. It's not perfect, but it can get you closer to the truth, right? So essentially 5 and I think it gets getting confused between 5 and 8. It has which one has twice is 1. Yes. So apparently there are a lot of ones which is tilted to the right, right? And there are a lot of ones which are straight, So again, it doesn't know there's 1 or 2 or 3. It is just looking at pixels. And based on pixel, it is actually it's clustering them. It doesn't know that there are 10 different type of digits there. It's just purely looking at pixels. And based on that, it is able to say there's a 2, there's a probably 9, 8, 3, 6, 4, 0, and 2 type of ones, and this probably is 7. So that, it's still quite good. In a way, as I think I mentioned that it will get you to the 80-90% of where you want to be, right? So the question is whether you want to stay at 0 or you want to get to 80-90%. So this is not perfect, right? Unsupervised learning, it will not be perfect. This is with the 5% data. We can try with more data also. So in this case, what I can do is, there's a train X, images, I can feed images, that's the name of the, right? So if I do that, you guys will need to stare at the screen for maybe a minute or two. Right, it's still running. So here it is showing that, you might have a lot of pictures also, right? In different domains. So it can become hard to apply k-means on pictures. Because it's so slow. Imagine if you want to apply it on real life pictures, like maybe say 1200 by 800 pictures, right? Those are the regular sizes of the, So 1200 by 800, how many features then we will have? If it is 1200 by 800 picture, how many features we will have in each picture? 960,000 features, right? So usually in structured data, we don't work with too many features, like maybe maximum 10, 15, 20, right? If you look at structured data. But in unstructured data, your number of features just explode, right? So that's another thing with the unstructured data, because you don't know what to do with all those features actually. So it is still running. So now at least it should take 60 seconds. Maybe it'll take more. It'll take more, and it's not by 12. It might take 2-3 minutes or more maybe. And so what it will do, what it is doing actually is basically it is calculating the distances for each data point, coming up with a centroid, then readjusting, then calculating the distances again, and so it will run for a while. All right, so we'll let it run. So this is, so basically the hope is like, if you feed it some other type of images, like we talked about the medical images or something else, hopefully it can, cluster them in a nice way so that those clusters start to make sense. Okay, so it is done. So it took about 161 seconds, 2.5 minutes, a little over 2.5 minutes, right? But not bad. But we can go ahead and display. It is still confused with 1 and 1. There are 2 zeros. Yeah, 4 is missing. So it is confused. Sometimes it gets confused between 4 and zeros also. Right? Yeah. And if the pictures are bigger size, that might help it actually. Because the pixels will be a little farther away and it will be easier to kind of make out differences. But these are small pictures. So the distances are small between pixels of different images. Right? So that's another thing. But again, to say that it basically got 0, 1, 2, 3. It did not get, 5 is also missing, 6, 7, 8, and 9. So it got huge. That's what I've seen is 8 out of 10. As I said, about 80% you can get. You can try different, distances or, different ways, but usually, you cannot really truly control it, right? Because you yourself don't know the data well. So we can try to see if we can increase number of clusters to get all the values, right? Now, but then you will have maybe 2 or 3 times 2 and all that, so you have to deal with that as well. Right? So, but it might be useful in real scenarios. Maybe suppose when we say medical images, it might say, stages of the tumor, but it might also say, stages of, stage 2, this is for male and this is for female. Just like this, 1 is tilted this way and 1 is, so the numbers could mean, basically further dividing your data, right? Based on the age also. This is stage 2 for, over 60 years old people, and this is stage 2 for less than 60 years. So now let's see what does so what cluster should we look at? We can look at cluster number what is this? 3? 0, 1, 2, 3. 3, right? That 8 is, I'm sure it will have values from both 5 and 8. If we try to look at cluster number 3, and now we are looking at the labels. What kind of labels are there? So let's try to print it out. Okay, what happened? Cluster label 60,000. Okay. Where is the train Y? Okay. I should use labels Y, because we changed from train X to 6,500, and so in cluster number 3, which is this basically fourth cluster, we have 3,462 8 and 1,486 5. So that's where it gets confused, because 5 and 8 kind of, it's just missing one small curve, otherwise they look very similar, and that's why it gets confused, right? You can see that, I mean, even with 3 also it gets confused a little, right? Because 3 is kind of a half 8. so you can see where it gets confused and where it makes sense. I mean, so this is how we can actually, I mean, we're just trying to compare where it is getting confused, but this is how you can use k-means to do your clustering on images. Clustering on images, which can be powerful. You can try it on your home images also. You will have a lot of images, everybody takes a lot of pictures, and see if it can, maybe cluster pictures based on occasions or different members, or, we can see that, we can do that. That'll be a fun thing to do, right? You don't need to wait for anybody's data. You can try it on your own pictures. And now what we can do, we can just go do the same elbow method. We can try that and see, where the loss is the lowest. Okay, I'm using train X, only 5% of the pictures. Otherwise, 2.5, and it's basically going to run for almost 19 times. So we are going to look at 9. I don't know why I put 19, but so it's going to run a lot of times. So you can see that initially the loss is reducing. It'll keep reducing. You can take SSE to 0 also. And how do we take SSE to 0? Sum of squared errors can be 0 also. That is the lowest loss possible. Right? When does that happen? Each data point is a centroid of its own. Right? Or basically, each point is a cluster. There's only one point in the cluster. Right? That's an exam question. Right? So now it is basically coming down. We were at 10, it was around 754, what is the millions? And so it's coming down. Or any question as it's running at this moment? Any questions? Why we are calling it unsupervised when we are still training the model? So training will happen no matter what. So first of all, in machine learning, training will happen with the data, whether it's supervised, unsupervised, or reinforcement, right? In all these 3 type of learnings, training will happen. And that's how we also learn. We just don't recognize it. We humans also train ourselves in the same way. We keep observing and looking at different things. We read a book. We read a book like a textbook, or maybe we have to give exam on that. So we read it once, and then we go back to it again. Why? To train ourselves better. Right? We go a third time maybe. Let me practice it. We keep doing that, and still we do not score 100 in every exam, right? No matter even all the questions are coming from that box, still we do not score 100. So same way, we show data to the machine, and answers are there, but it's impossible for machine to score 100 for machine also. Usually you might get to 99.999, but there is nothing like 100%. 100% will mean 2 things. If you're getting 100% accuracy with your model, there are 2 things. One is basically, you have, an overfitting situation where basically, it just memorized things. My machine just memorized the things, and it's not really learning, right? That's one thing. Second thing is there is some error in your program. Go check it, right? That's another thing. Sometime it will show 100, or you'll be happy, and then you debug. Oh, there was I just gave it one label, so it will be 100% anyway. Right? Okay. So again, the elbow method, what we see here is again will not be exact elbow. That's what I've seen in practical. Although we say it will be a nice elbow, but so we have to kind of choose where somewhere here, where it makes sense. And in this case, 10 is that what we are looking for, but it could mean different, things maybe. All right. So any question, so we can apply k-means on structured data as well as unstructured data. We saw the images, right? We can cluster things, right? Now, question is, now next thing, so we always cluster things and so we saw the, with the customer segmentation. We will look at one more example of images where we try to make little bit more sense out of these clusters, or rather use these clusters in a more useful way. So we can use clustering to reduce the size of the image as well. And I thought that's not my idea, by the way. That somebody tried it, and I thought that was a nice, basically that, we have to think how all we can use clustering, right? So let's look at that example and what it means. So it is called color quantization. So let's look at that example. What we mean by reducing the size of the image. All right. So next is color quantization. So how that color quantization, so let's look at that, a very nice example of using clustering to reduce the size of the image, which could be very useful. Suppose you are transferring the data in low data areas and where bandwidth might be a problem. So what you can do, you can convert your image, you can reduce the size of the images and send it out. So let's see how that works. Okay, so we're going to use this on one image only. Anyway, the same program can be applied on any image. So first of all, what we will need is some image. So we're going to use one image available within Scikit, and it's called China. So there's and so we have, all right. And this is again, the image is loaded as a NumPy array. Right, when we read it, and the shape of the image is 427,643, which means, what does it mean? It means usually when we read the image as NumPy array, height will come first, then the width. Usually you have width, height, and then depth, right? What does this 3 means? 3. It's basically those 3 channels, red, green, and blue. Each pixel is represented by 3 values. 1 for red, 1 for green, 1 for blue. Why we have those 3 values? Basically, the idea is that we can create any color using these combination of these 3 colors. And how do we combine? How do we change red, green, and blue? Changing the value of that, like 0 to 255. If you keep it 180, that's lesser red than 255, the red value. So you can have almost, lot of colors in your pictures because they differ by one value, one number only. Like one pixel has 255, 255, 255. All 3 of them are 255. That means it's white. The other next pixel might have 3 values as 254, 255, 255. That's still a different color. That's a different color, right? Sometimes our eyes are not able to distinguish though. So we can take advantage of that and reduce number of colors in the pictures. So that's quantization, means basically we are basically clustering all the colors available in a picture in fewer colors and still showing the picture. And it looks pretty close to original picture. It looks very close. So that's what we will see. All right. So we have a picture, we have the data, which is you will see that. You will going to see that. Okay, so first let's look at the original image, right? So we are using Matplotlib again, and let's look at the picture, and this is the picture. Quite complex picture, lot of colors there, and nice picture, right? It's very rich in its color and all, right? So now how many numbers does it have? It has 427 by 640 by 3. That many values. That will be numbers to represent the picture. Right? 427 by 640 is the number of pixels, and each pixel is represented by 3 numbers: red, green, and blue. Does that make sense? It has how many pixels does it have? We can do that. Python allows us to do this very easily. 640. So it has 270,280 pixels. And each pixel has 3 numbers to represent it. One for the red, one for green, one for blue. Okay? All right? So this is the picture. Size of the picture is 427. In fact, you can see it here. 427 is the height. 427 pixels is the height. And 600 and what is that? 50? I guess 640 is the width. You can see here with the axis values. Now here we have only one image. Here we have only one image, not 60,000 or 3,000 records and all. One image. So how many data points do we have? How many data points do we have? So what should we consider as a data point? In this case, so what we are trying to do, what we are trying to do? What is the goal of this exercise? Color quantization, right? Reducing the number of colors. So each color is a data point to me. In this case, each color is a data point. And what is the color? What is the color in this case? So we said it is 427 multiplied by 640 multiplied by 3. This is the height, this is the width, and this is the depth of the image. We have only one picture. So we are not working with a lot of pictures here, just one of them. Right? And what we want to do, so this is a little mind twisting. I mean, we are used to calling our data points either as a picture or a customer record or something, right? Here we are saying only one picture. And we say clustering, of course, requires at least more than one example, right? Otherwise, what is the point of clustering, right? But in this case, what we want to cluster is colors, not the picture. The colors in the pictures, right? How many colors do we have in this picture? No, that's a good. So, what makes a color? RGB makes up a color, right? Let me rub it off. I think this example makes us think in a different way also, right? I mean, as I said, so and we are all creative people, and I'm sure we will come up with similar examples of our own, right? So a color is, now we are not talking about an image. Image just happens to be, what is an image? Image is nothing but a combination of colors. You put different colors together and it becomes an image. So you have lots of colors. And color is basically, we say, is made up of value of R, G, and blue. So red, green, and blue. Right? So if we combine these colors in different quantities, we get new colors. Right? So we need basically 3 numbers to represent a color. A number for red, right? Maybe between 0 to 255, that's what we usually use. Another for green between 0 to 255, and then same thing for blue. Right? So what represents a color is this. Right? In this picture, if you see, at each point, there are 3 values. So each pixel is our data point, and it has 3 features: red, green, and blue. So how many data points do we have? How many data points do we have now? It was, I think, 273 something, 273,000 something plus, right? Basically 427 multiplied by 640. That many data points we have now. And 3 features for each of those pixels. So now, rather than image, the pixel is the data point. And we have a lot of them. 273,000, that's a lot of, features to work with. Sorry, a lot of data points to work with. We have not worked with these many data points in any of our examples so far, right? Suddenly with one picture, we have a lot of features, right? Sorry, with a lot of data points. All right, so that's what we will do. And so we have, how many colors do we have now? How many colors do we have in this picture? So, not many colors. We have exact number with us. What is that exact number? No. It's the number of pixels. Each pixel is a color. Each pixel is a color, right? And we know how many pixels we have. 640 multiplied by 427. So we know exactly how many colors are there. Some of them could be duplicate colors though. So unique colors could be less than 273K. So we can check that. If all three numbers are equal for different pixels, then we can say, okay, those are duplicate colors. And there are some duplicate colors over there, right? We can see that. The colors, essentially, so unique colors will be less than 273K. But still, it will be a good, huge number. So now what we want to do is take this all 273K colors or maybe 200K colors. Let's see, there are 200 unique colors. And reduce it to only, say, 16 colors. From 200,000, we reduce it to only 16 values of colors. The image can have only 16 different values of RGB. That's all. From 200,000 to only 16. So we are going to cluster all these 273K pixels into only 16 clusters. And then we replace the original pixel. We replace the original pixel with the clustered centroid of the centroid of those pixels. Clusters. So only 16 colors will be possible to be drawn. But we will still draw 273,000 pixels because that's what the image is made of. But we will only use 16 colors to draw them and not all those combinations. Okay? And then we will see, does the picture look okay? It will not be exact though, right? 200K versus 16 is like, massive drop, right? But let's see what we can do. The real world will be that basically what you can do, suppose you need to send out a lot of images to the, where your data bandwidth may not be available. So you are compressing the image. You're compressing the image. Say if you have a 2 megabytes image, you can compress it to 100 KB. How? We will see. Why I'm saying that we will come back to that. But let's see why we are saying that size of the image is reduced. Right? We will talk about that. Okay? So now we have this image. So what we are going to do is we are going to build a k-means clustering, and so now we can get the height, width, and image of the shape of the image, and we are going to. Why are we reshaping the data? So we have three-dimensional data, right? We have height, width, and depth. So what we are doing here with reshape is basically we are multiplying height and width. So we are making our data as 273K, 3, two-dimensional. 273K data points and 3 features. This is features. Make sense? Why we are doing that reshaping of the, basically what we are doing is, we are saying that we have these many pixels, both multiplied, and each pixel having 3 features, right? And then we are ready to do the clustering. All right, 273K, that many, and let's cluster it in 16 of them and see how much time it takes. So it may take a bit of time. So we'll need to wait. Now, So now let's try to address why the size will be low. As we discussed, the image to a machine is nothing but bunch of numbers. Bunch of numbers, right? And in this case, how many numbers in the original image, how many numbers that machine need to store? It's storing numbers basically, right? That's all it's doing. When we say there's an image, it is nothing but those numbers stored in a file. We may call it JPG, PNG and all that, right? But it's those bunch of numbers, those RGB values stored in a file. So how many numbers are we storing if we look at roughly? How many numbers are we storing? 273 multiplied by 3. That many numbers. There might be some duplicates. So you have a lot of these algorithms like PNG, JPG and all that. What they try to do, they try to compress the image using some algorithm. Maybe remove the duplicates. Just keep information about that if there is a duplicate. So rather than storing 3 numbers, just store 1 number and information about where all this number appears. Right? So we use those algorithms to reduce the size of the image. Right? But for simplicity, we say that now we need to store 273K multiplied by 3. That means about 819K. We will say 819K. That many numbers we need to store. Now, if we reduce our colors to only 16, how many numbers will we require to store? So 16 into 3, basically 16 colors are there. 16 colors are represented by, each is represented by 3 numbers. So 48 numbers definitely we need to store the colors. And for each pixel, we can have just one number to say, okay, which color should we have here? Right? So it will be 273K, those numbers, right? Because at each pixel you need to put a number between 0 and 16. Hey, this belongs to, here color 0 should come, here color 1 should come, color 2 and up to color 15, right? 0 to 15. So that's all we need to store. So 273K and plus 48. So that many only, right? So in a way you're reducing almost by 1/3 the size of because your number of how many numbers you need to store has come down by almost 1/3, has become 1/3 of original numbers, right? So does that answer your question? I mean, why we are saying images size is reduced? Actually machine learning is getting into a lot of this image processing. For example, and this is a big one. I mean, basically you have a 4K resolution video. 4K resolution video, right? So obviously it will occupy a lot of space. So you need to download, suppose, nowadays everything is moving to cloud, right? We don't buy these DVDs or CDs anymore, right? We just basically go to Amazon Prime or Netflix or some other place and then say, okay, I want to play this video. Now, when you download it, I mean, you're downloading GBs of data, gigabytes of data, right? Because these are high resolution images. And so video is also an image. Everybody knows that videos are nothing but a lot of images put together. It could be, it starts with about 30 frames per second or 30 images per second. If you show 30 images per second, it feels like things are moving, right? And then you can keep on increasing it to more and more. And after some point, eyes stop recognizing that you're increasing the frame rate or number of images, right? So now that's taking a lot of bandwidth, and bandwidth is limited. Right? It's expensive to build, keep building high, more and more bandwidth to transfer this data. So what we can do is we can basically compress these images in a much smaller resolution using machine learning and download those. So gigabytes becomes maybe kilobytes or megabytes. And then on the client side, we have another machine learning model which can again increase the resolution of your image. Increase the resolution of your image so that it becomes 4K again, right? 4K again, right? Or some fun thing like you have, some of us might have those black and white pictures from old era, right? When there only black and white cameras existed. Or like I got married in 2000 and we didn't have digital, pictures taken that time. So all my wedding photographs are, it's in paper, and I can digitize it by scanning them. But there's a lot of those spots are there now because paper deteriorates over a period. You'll have dots and all. Now, how do I remove those dots? We can use machine learning to kind of clean it out. Clean it out for me. Once I scan it, it becomes digital. Then I can use machine learning to clean it out. It becomes a brand new picture as if I got just married just yesterday, right? So the lots and lots of possibilities out there. Sometimes with machine learning, we focus on what we are doing right now, right? At office, hey, let me try to automate it. But with machine learning, what is changing? More and more things are possible to do using software. That's where the real value of AI and machine learning comes into play, where you are able to do things which were not possible earlier, right? I mean, if you just a simple example, if I need to remove those spots from the digital images, it was a major undertaking. Nobody was taking it up basically. And now I can do it with just a click of a button, right? So think of those possibilities. So I hope that answered the question. All right. So so it has run. It took about 56 seconds. Still pretty good. So now let's look at. So now we're going to predict the cluster for each of our pixel. What cluster belongs to which? Cluster value to each pixel, and it will give me 273,000 numbers. So these 273,000 numbers are nothing but values between 0 and 16. We can actually look at that. Labels, and maybe let's print first 15 of them. All of them are 6. Okay, that's nice. And that's okay, I guess. But the reason, so that was also first time I did this. I was surprised that how come all my first 15, 20 pixels are assigned to same cluster. But in this case, it makes sense because suppose if you start here, this looks same. Looks same. So same cluster, right? That's why you will see that maybe so now I have that unique. What are the unique values in this labels? It's between 0 and 15, right? 0 and 15. So each pixel will be assigned one value between 0 and 15. So those are the numbers. Now our colors, what are our colors? Is basically we can get it from the centroids. The new colors are nothing but the centroids of the 16 clusters. So we get that, and of course it is 16 by 3. Each centroid is nothing but a color with 3 values in them. And so we can, of course, look. These are the 16 values, right? These are 16 values. Again, these are colors, RGB. These are RGB. And so what I'm going to do is I'm going to basically rebuild that image. So I will replace each RGB value in the original image basically with the value of the cluster centroid. Right? That's what I'm doing here. And now, of course, shape remains same, 427, 60, 640 by 3. And this is a big, array. I mean, again, nothing to see here, but the interesting thing happens here. Now I'm going to display 2 images, one original and one quantized from 200K to 16, and let's see how it looks. So this is the image. So on the left side is the original one, and the right side there's a quantized one. So slight distortion in here, but otherwise it's manageable, right? So this is, just with 16 colors, I'm able to, without any supervision, I'm able to basically, reduce the size of the image and still display the size. right? Does this make sense? So do we want to take one more exercise, or let's do one more exercise, and this time we will do with the text documents. We have not applied k-means to, we have applied k-means to structured data, we have applied it to we have applied it to unstructured data. In unstructured we applied it to visual data, and now let's see if we can apply it to text data also, right? So we have a lot of text out there, especially in visual. I mean, we don't work with that much in current corporate worlds. Why? Because visual was very hard always. You had so many features, millions of features to deal with each data point, and nobody could make sense out of it. But now, as we are getting more and more vision power with machine, we will start seeing those companies which use vision to do things, right? If somebody comes, I can tell what the person wants just by looking at the person, or something like that, right? So now let's look at an example where we are going to use we're going to basically use clustering on text documents, right? So let's let me first shut down because all right. So we are going to apply so text documents, a bunch of them. And what we are going to use is this news group data, 20, so what is that news group data? Have you used it before? Yes or no? Basically, there are a bunch of, these used to be news groups where, old news groups where people can send, their thoughts or questions for 20 different categories. 20 different categories. So we basically, what are those categories? Maybe we can just check that out first. So in scikit-learn you have this data set fetch 20 news groups. So I'm going to pull out only 4 categories, but we can check what is this data set. Let's fetch all the categories. Yeah, you will not. Okay, you're not seeing. Okay, but anyway, don't worry. When you run this command, it will actually but you can, when you run this command, it basically gives you it downloads it from the internet. All right. So, and we can then check what are the categories that are available. The attribute name is target names. Once it runs, once it downloads, I should be able to print. So there are 20 different categories. That's why the name of the data set is 20 news groups. And so different categories. So I am going to pull out the documents which belong to, say, sports or baseball, and religion, graphics, and space. So we there are different categories of documents. So I'm going to pull it from 4 of them and see if clustering can be done across these 4 groups. I mean, if we throw all the documents at clustering and see if clustering k-means can then try to cluster them in 4 different clusters, and do they make sense based on the data, right? Now, before we go there, so how do we feed a textual data to machine models? How do we feed? So image we saw. So in the structured data, with what we saw was we had the numbers. We had the numbers, and we can feed it to the machine just as is, because machine model can work with numbers, right? Machine learning is pure mathematics, and they just work with numbers. So no need to kind of change it to any other format. I mean, you can massage the data, you can do feature engineering, but it's still numbers. And with the image, so what were images to the machine? Images to the machines are nothing but those color information, RGB values, right? So again, bunch of numbers only. But that's not the case with text. Text, although they ultimately they get stored as zeros and ones, but in programming languages they are not numbers. They are, yes, ASCII characters. So how do we feed text data to machine model? Because machine model expects numbers only. If you throw text at them, they will just throw out an error. So how do we feed text data to machine models? Have you guys gone through that training already or not? Sessions? No. Okay. So we will need to convert our text words. Basically, the word text is nothing but words, right? Words written after one another. We will need to convert words into numbers before we can feed it to the machine. Before we can feed it to the machine model. I shouldn't say machine model, right? Now, how do we convert that text to numbers? How do we convert text to the numbers? So you guys want to look at that quickly, or want to keep it a kind of a black box right now? I mean, that's not part of this class, but I can spend 10 minutes on how to convert, 10-15 minutes to convert, and then because we will need to do that anyway. I can just press a button and it will happen here with scikit-learn, and you don't know what happened, but it'll give me numbers. But if you want to understand what happened, I can spend 10-15. Maybe I'll do that. Let me do that. Okay. So wget command. Okay. What is the? I mean, you will need to check. Maybe just Google it, because wget is kind of a utility. Otherwise, you can just download it manually. You can just do download if you're and try to fix it later. Okay. So where's the? Okay. Let me see if this works on this or not. Oh, good. All right. So this is not part of this class. So again, we will not spend too much time, but that's okay. If you have question, go for it. So what I was saying, that you cannot directly feed your text data to ML model, right? You cannot use it for training or for prediction. You will need to convert it into numbers, right? So there's an additional step in case of NLP. When NLP is nothing but where we are trying to have machine understand the language data, right? So how do we convert text to numbers? So we will just quickly look at. So suppose we have all two documents, two text documents. One of them has document number 1. It says it has 2 sentences. He's a good boy. She's also good. And document 2 is Radhika is a good person. So don't worry about what is there. But there's some text, right? There's some text. Now, how do we convert it into numbers? So before we can convert it into numbers, first thing we have to do is identify the vocabulary of your data set. So if you have a lot of documents or a lot of reviews and all that, what you will do, you will first of course there are programs which will go read all your data set and come up, okay, these are the unique words in your data set. So in this case, these are the unique words: a, also, boy, good, he, is, person, she, Radhika. About 9 of them, I guess. Right? So first build the vocabulary, right? And then what you do is assign an index for each word in the vocabulary. Assign an index. Index means a particular number. So that the word is a number now. Number 0 means a, number 5 means is, number 6 means person in this case. Right? Again, it has to be unique. Right? So you assign an index. So that's the starting point. Now, how do I convert? So now I have converted my vocabulary into a number. Right? So vocabulary is converted into numbers. Now, what is the goal? Goal is to convert the documents into numbers, not the vocabulary. Right? So we will use the vocabulary. So how we'll do it? Let's say first, so let's say we want to convert document number 1 into numbers. Right? So he is a good boy, she is also good. So this is our index information. These are the actual words in vocabulary, and these are the indexes. Now document 1, we will see A. Is there an A there? Yes? So we can put 1A here because there's only one A. Also is also there? Yes, there's one also. And then boy is one, yes. Good is twice. So we put number 2 here. We put number 2 here, and this is how we can convert our document into a number. Document into a number. This is the simplest approach. Nobody does it this way, right? Nobody uses this approach. But this is good to understand to start with, right? So you basically converted, you replaced your words, you basically go by the vocabulary. You basically what you're saying, you're assuming that all the words in the vocabulary exist in my document, and you just count how many times they appear in my document, right? Same way we can do for document 2 also. Because document 2 is small, so you will see a lot of zeros. There is no also, and there is no boy, there's no he, so you put zeros there, right? But both document 1 and document 2 have same size, right? All of them are about 9 numbers, total 9 numbers being used. This approach is called count vector approach. You're basically counting and converting your document into a number vector, right? So this is one approach, simple approach, but a little more complex approach is called TF-IDF vector, right? TF-IDF vector, so there are basically 2 terms here. One is called term frequency. TF stands for term frequency, and IDF stands for inverse document frequency. Right? So let's look at how we do that. Right? Let's see how we do that. So you have basically, so first of all, what you do is you write down all the words in your document. So all the words in your, so suppose we are looking at document number 1. Document number 1. So you write down, so you have done that. So before, even in TF-IDF, you first do the vocabulary and indexing of each word. That part is done, so I'm not covering that again. You will do that part, and then to come up with a TF-IDF vector, you basically list all the words in your document, whichever document you're looking at, and then put in count number. So like is coming twice. He is and she is. So 2 times is coming. Same way good is also coming twice. Otherwise all other are ones. There are total 9 words in document number 1. Right? Now we need to calculate TF. So we will calculate 2 things. TF and IDF. So TF is within the document. Within individual document. So what is the TF formula? Frequency of the word in a document divided by total number of words in the document. Same document. We are just looking at only the document, not across the data set. Alright, so suppose we want to do TF for HE. TF of he in document number 1, because he appears only 1. He appears only 1 divided by 9, because total number of words in document 1 is 9. So it is 0.11. Similarly, if I look at good appears twice in doc number 1, and total number of words still 9, so it is 0.22. Right? That's TF. Now, everybody okay, comfortable with this approach? Right? Just number of how many times it appears in the document divided by total words in the document. Right? Now, same thing we can do with document number 2. Radhika is a good person. And if I try to calculate, again, TF for HE, he, because I'm looking at 2 words, he and good. Right? He does not even appear in second document. So it's 0 divided by 5, because there are total 5 words in that document. Right? And how about good? 1 by 5, 0.2. Right? So now we have he and good TF, term frequency for both he and good in both document 1 and document 2. Right? Now let's go and try to understand IDF. Right? So for IDF, we will look across all our data. So in this case, we have 2 documents, so we have to look at all the documents in our data set. So we have listed, okay, this is our document 1, document 2. Now I need to calculate IDF. So IDF is log of number of documents in your data set. And how many documents do we have in this data set? 2. Divided by how many documents that word appears in. How many documents that word appears in. That's IDF. So now let's look at IDF of HE. Now, as I said, IDF is across the data set. TF is specific to that document, right? So IDF is, for he is log of 2, why 2 is the number of documents, and 1, he appears only in one document. He appears only in one document, it doesn't appear in second document, so it's log of 2, which is 0.301. Right, you can calculate it using calculator. Similarly, what will be the IDF of 2? What will be the IDF of 2? Oh, sorry, good. IDF of good. Okay, I think I made a mistake there. No. Okay, not 2 by 3. Sorry. Okay, not a mistake. Okay. Number of docs is total docs is 2. That we know. But how many documents that word appears in? It's not the frequency. Word in number of docs. 2 only. So 2 by 2 is 1. And logarithmic of 1 is 0. Right? So what does it mean to say, hey, this IDF is 0 of good? Why is IDF is 0 of good? Okay, math-wise we know 2 by 2 log of 1 is 0. But what it means, to think of it, see, good appears in both the documents. Which means good is not a word which we can use to distinguish document 1 from document 2. Because it appears both places. It's like a stop word, the, a and all. Those things appear in all the documents. So automatically they will get very low score. Right? So that's what we are doing. And basically, so now when we want to calculate TF IDF of he in document 1, we first get the term frequency multiplied by the IDF, and then you get this value. Good will be 0 anyway because it's the IDF is 0 and he in document will be 0 because the TF is 0, and good will be 0 because IDF is 0 anyway, right? So this is how basically we can build our TF IDF vector. So we have just done for good and he. Similarly, we will do it for A or all the words in the vocabulary, and this is how we can convert words into a document into numbers. I mean, again, you probably will revise it at some place. You will have, so don't worry. I mean, just maybe next time you know how to do it briefly. And again, we don't have to do all this by hand. There are functions available in scikit-learn to just press a button and it does it for you, right? So that's what we are going to use. We are going to use TF IDF to convert our news items into numbers, so that we can feed it to k-means or any other algorithm, right? So you will do that. Okay? Hopefully it was useful. So now we basically I downloaded the whole data set because I executed this command without giving it the categories that I want to download. So it has downloaded about 14 MB of the data, and these are the categories, 20 different categories, some on PC hardware, Mac hardware, hockey, baseball, motorcycle. Again, this is a US data set, right? Some are on religion, again, politics, guns, Mid-East, Christians, electronics, different topics, right? So what we are going to do is we are going to basically use only 4 categories for our analysis. And so that's what I'm going to do now. I'm going to remove this part and so that you, okay. So now I get only 4 categories and I download the data set. Anyway, because the data set is already downloaded, it was pretty fast. Now to understand the data, how many documents do we have? We have 2,151 documents in our data. So overall, I think it is about 10,000 or maybe 20,000. Yeah, if you can try downloading the whole data set and see that. And if you want to check out any particular post, we can do that. I mean, this is one post. So it was more like a new, email, email group. This is from email group. Different groups were there in the, usually you have those Google groups and all, right? Similar thing. So, for each topic there was a group. So the data is picked up from that different groups, right? So here it's a little clumsy, but you can it said, didn't Bob Horner go straight from Arizona State University to the Atlanta Braves? And because I know Atlanta Braves is baseball, this probably belongs to baseball. And we can check that. We can check the target, which post belongs to what category, right? So if I say the 300 post belongs to category number 1, what is that category number 1? We can look at the target names. So first category is comm graphics, second category is baseball. And that's where this post belongs to. So this is a document with the baseball as a topic, right? So we can check other things also if you want to. So this is what we basically, so this is the data set, 2000 plus documents and 4 different topics. Again, we are not going to tell k-means that, these are the topics. What we are going to ask k-means, hey, can you go ahead and cluster these 2000 documents in 4 different groups and then see what those 4 groups have. Do they make sense based on the category, right? So that's what we want to do. Basically, can it cluster things as we expect, right? So we have a way of validating how well k-means is doing. Just like with MNIST, we were able to validate, okay, it works about 80% of the time, right? Same way here, because we know the actual topic, we can compare, right? So we are the domain expert with this. We have the domain expertise in this case, right? So I'm going to first convert text into numbers, right? So how do we convert text into numbers? Is basically first we take, you can get this TF IDF vectorizer, just like what we described just now. And so we are going to consider only 10,000 top words, because there will be a lot of words. So one thing you will, when you convert text to numbers, you will have to do is, you will need to usually limit your vocabulary. And why is that? The main reason to limit vocabulary is to basically you will not have enough computing power. Because if you remember in TF IDF or count vector, each document was how big? How many numbers each document had? Sorry? In the one example we saw. Here, we said 9, right? 0 to 8. But why 9? Number of unique words in your vocabulary. So what we are saying here is keep unique words to only 10,000. Because your documents will be 10,000 numbers, each document. And here we have 2,000 documents. So it will be 2,000 multiplied by 10,000 metrics. So, you will need a lot of memory. And it might throw an error. It worked on my machine because I had GPU and a lot of memory. So we need to see, we might have to reduce this further to say 5,000 and all. But we'll try it out with 10,000 numbers, 10,000 unique words. And you're just removing, English stop words like A, B and all that kind of stuff. Okay. So, and let's fit the data. So then we provide the data to fit. Admit, okay, so it's done. And we can look at the shape. What will be the shape of the output vector? Output. We have fed it 2,151 documents. What will be the shape we just discussed? Multiply by 10,000, right? And that's what it is. 2151 multiplied by 10,000. So how many features are we dealing with here? We're dealing with 10,000 features. How many data points we have? 2151. Right? That part is clear now. Right? This is similar to MNIST, not the color quantization. Right? So now we can apply k-means. And we are going to do 4 clusters because we know we want to check it out, 4, right? So let's go ahead and do that. And it may take a bit of time, again, because there are a lot of features. But a lot of them are zeros. That's one problem with TF-IDF. A lot of them will be zeros because both TF-IDF and count vector assume all words are there in each document, but that's not usually the case, right? So you will have that problem. So it has done it. Now we can look at the clusters. So 4 clusters will be there, and these are the value. How many features each cluster will have? We have 4 clusters. How many features each cluster will have? 10,000 only, right? So 10,000, it will have TF IDF value of each of the 10,000 words. TF IDF value of each of the 10,000 words, right? So it also has information about words. Now, higher the TF IDF value, more important is the word. We know that. I mean, higher because higher value means you saw that a lot of them were zeros. Why? Because either it doesn't exist or it exists in all the documents. So a higher TF IDF value means important point. So what we can do is, if we can get the words, the important words from each of the centroid, how do we validate whether it makes sense or not? What we can do, because centroid is a representation of 10,000 word, and I can try to check what words are important for these centroid. So I can try to see what are the top 10 or 15 words in this centroid, which have high TF IDF. Then I can look at those keywords basically. What are the keywords in each cluster? In each cluster, what are the keywords that it is looking at? Where it is assigning high values, right? So that's what we can do, because we cannot say, hey, this belongs to politics. We have to look at the words and then say, okay, these words belong to a politics topic, then it makes sense. Or it belongs to baseball, it makes sense. Or it belongs to space. Like if the word like NASA comes in, we can say, hey, that most likely is space type of topics, right? That's what we can do. So what we want to do is we want to get the get the words where TF IDF is highest for each centroid, right? So how do we do that? So what we can do, I don't know if you have used argsort. There's a method called argsort. Have you used it? No? Okay. Maybe what I will do, I'll just do a simple example so that it makes sense, because we are going to sort 10,000 numbers, right? So so let's say there's a numpy array. Okay, have I imported numpy up or no? Okay, I need to, let me import numpy. This is just to show a simple example what argset does. Okay, so numpy is there, and then I'm going to have a simple array, np.array, and we will say 2.1, 4.4 and 1.1 and say 0, right? These are the 4 numbers that I have in my array. Just like in centroid has 10,000, I have just 4 numbers. And now what I want to do, I want to apply argsort method on this numpy array. A.argsort. And let's see what results we get. So we got 3201. How do these numbers relate to this thing? Let me make it clear. How do these numbers 3201 relate to the array? These are the indexes. And why 3 is coming first? Ascending order of values. So that's what argsort does. It basically gives me the indexes. It gives me the indexes and it gives me indexes where the values are first the lowest value, then the bigger one, the bigger and the biggest. So third means this is 0, 1, 2 and 3. So 0 comes first. The index number 3 comes first. Index number 2 comes second. Then index number 0 comes third, and index number 1 comes last, because that's the biggest one. That's what the argsort does, and that's what we are doing, right? Now what I want not in ascending order, rather in descending order, because I want to look at the top, say 10 or 15 words in my centroids. So how I can reverse it is by just a kind of a simple technique. We can just provide colon colon -1, right? And what it does, it basically reverses it. Okay, sorry. I should say a dot arg sort. And then do it. Now this 3201 becomes 1023. So now I got in the indexes in descending order. Now, so that's what I'm going to do. So because I'm going to sort it on TF-IDF in descending order for centroids, right? So that's what I'm doing in the here. First, I'm sorting it in ascending order, getting those indexes, and then reversing those indexes using this simple technique. All right. So now we can do that. Now, what we want to do is get the vocabulary from TF vectorizer. Hey, what are the words in vocabulary? So we can actually, there are a lot of words, and we can actually look at how many words are there. So how many words should be there? TF-IDF. How many words are there in our vocabulary? Okay, so the answer should be 10,000. Let's see. Right, 10,000 words. Right. So, and these are arranged with in the order of how they appear. Okay, the indexes. So we have the indexes from centroids, and now we can try to extract those words from these vocabulary, right? So let's try to display. So what I'm doing is I'm just displaying the top 10 words in each cluster or each centroid, basically. Top 10 words in each of those 4 clusters, right? So let's go ahead and print them. Okay. So cluster 1 has words like space, NASA, Axis, Henry, EDU, Alaska, that kind of thing, moon, Pat. So what does the cluster 1 belongs to? Like one of the categories. So what are the categories we can? Okay, I have that. So let's look at what are the categories in our data set. We have graphics, baseball, space, and religion, right? So this one definitely shows me that hey, this belongs to space. These documents in this cluster most likely belong to space category, space topic. Next is graphics, EDU, clients, com, subject, organization, university, posting, host. So more to do with computers. Looks like more to do with computers. And that's the category of computer graphics. The third is EDU, baseball, year, team, game, players. This is definitely sports related, and this is related to baseball. So we have that third one. And the fourth one is God, Jesus, Christian, and all, morality, definitely something to do with the religion. Right? So we can see that actually K-means was able to cluster these documents, text documents, without even knowing what these documents were, and it did a pretty good job. Right? Agreed? Or right? So basically, we can use this sometimes we get a lot of customer feedback, and we may not know how to we have to go through each feedback and see, okay, this is a good feedback, this is a poor feedback. Maybe you have thousands of survey of feedback. Then you can apply K-means on them, and it might cluster in, say, 2-3 categories. And then you can say, okay, this is like a good part, this is a bad, poor feedback, this is neutral feedback or whatever, right? That's how we can use K-means to kind of get value out of the data that we have. All right? Everybody clear? So we have applied K-means on structured and unstructured visual and text data, language data, right? So we have covered the whole spectrum now with unsupervised learning, clustering basically.
This brings us to the end of this tutorial on unsupervised learning. So before you guys sign off, I'd like to inform you that we have launched a completely free learning platform called Great Learning Academy, where you have access to free courses such as AI, cloud, and digital marketing. So guys, thank you very much for attending the session. Have a great learning ahead.